In this video, I'm going to cover chapter 1 of my stochastic modeling book. That's the chapter about the basics of measure theory and probability. So here are the different topics we are going to cover more precisely. I represented this using a directed graph to underline the connections among the different topics. In case you are interested in only a specific part of this video, check out the thumbnail of the video that's going to show all the different topics or all the different parts of this video and exactly when this part is going to cover, so you can skip directly to the part you are interested in. So first, to motivate measure theory, I'm going to tell you about the limitation of the integral of the Riemann integral. So the Riemann integral was the one used until the end of the 19th century. And to illustrate the limitation of this Riemann integral, I'm going to tell you about a very simple probability problem that we are going to try to solve, but we'll end up with a probability that takes the form of an integral of a function that is not Riemann integrable. So which means that in the Riemann sense, this probability does not even exist, which of course is a prime. The limitation of the Riemann integral were not just in probability theory, that was a prime across mathematics, and many mathematicians tried to redesign a better integral, and eventually at the very beginning of the 20th century, mathematicians, so Henri Lebesgue and Émile Borel, came up with a new branch of mathematics that we now call measure theory that redefined the concept of integrals, and in their framework, many more functions are integrable. In particular, using their framework, we'll be able to answer our probability problem. So next, of course, I'm going to define all the main concepts in measure theory. We are going to start with a lot of basic definition. The definition of sigma algebra. Elements in the sigma algebra are called measurable sets. If you combine a set and a sigma algebra on this set, you get a measurable space. Then concept of positive measure. You can define on a measurable space a positive measure. That's basically a function defined on the sigma algebra. And this measure is going to more or less measure the size of the sets in the sigma algebra. Combining together measurable space and positive measure, you get a measure space. In parallel, you can also define measurable function from a measurable space to another, and you can use eventually your positive measure to, I would say, measure a measurable function, and by the measure of a function, I mean the integral. And then eventually we end up with a new concept of integral that's going to be the integral of a measurable function with respect to a positive measure. In the particular case of what we call the Lebesgue measure, that's the measure that looks at the length of interval, we get a natural extension of the Riemann integral, except that with the Lebesgue integral, many more functions are integrable. In particular, using the Lebesgue integral, we'll be able to answer our probability problem. So that was at the very beginning of the 20th century, and a little bit later, Andrei Kolmogorov had the idea of reinterpreting all the concepts from measure theory, but in the context of probability. In particular, we'll see that in what we call now the Kolmogorov model, that's modern probability, you can think of measurable sets as events, okay? You can think of measurable functions as random variables. You can look at particular case of positive measure with total mass equal to 1, and we get what we call a probability measure. And you can look at the integral of a random variable with respect to a probability measure, and that's what we call now the expected value. Okay? So you can redefine all the concepts from probability theory using measure theory, and you obtain basically a better model that is now modern probability. Okay? So then after, I'm going to describe a few tools that we can use to compute basic probabilities of some events. So there are three main tools. The first one is combinatorics. You can count number of outcomes in events to find the probability of simple events. If you have to deal with more complicated events, you can use a Venn diagram to rewrite the probability of a complicated event as a function of probabilities of much simpler events. And a third important technique is conditioning. But I'm not going to talk about conditioning in this video. I will need much more theory to be able to define conditional probability and conditional expectation. And so I'm going to do that in the next video, that it's about chapter 2 of my textbook. That's the chapter about conditional expectation and distribution of a random variable. But in this video, I'm going to cover the first two techniques. So first, we are going to talk about the basic rules of combinatorics. Okay, basic combinatorics, I'm not going to go very far. That's also related to graph theory. I'm only going to list and prove the simplest counting rules. And we'll see that this can be used in the case of symmetric probability spaces. Then after, I'm going to tell you a little bit about Venn diagram that you can use basically to, again, rewrite the probability of a complicated event as a function of probabilities of much simpler events. Okay? And as an illustration of that, I'm going to give you also a proof of the inclusion-exclusion identity. That's the most popular formula in this framework. That's basically a formula that tells you how you can compute the probability of a union of events, which is typically difficult, using the probabilities of intersections of those events. Okay, after we are going to go back at the end of this video to very general measure theory, and I'm going to prove a couple of theorems that are going to be important later to develop the theory of stochastic processes, and in particular martingales and Markov chain. So first I'm going to tell you about the monotone convergence theorem and the dominated convergence theorem. So the conclusions of those two theorems are the same. Those two theorems deal with sequences of measurable functions, and so you can look at the limit of this sequence, and a natural question is to know whether the integral of the limit is equal to the limit of the integral of the limit is equal to the limit of the integral. And so basically that's a problem about exchanging limit and integral. So we'll see that if we have some monotonicity condition, or if we have a condition of domination, then we can do that. Okay? In particular, the monotone convergence theorem is going to be used a lot in future videos about, again, martingales and Markov chain. I'm going to give you a complete proof of those two theorems. The proofs are not very easy, but they are not that long either. So I'm going to give you a proof of the monotone convergence theorem, and from the monotone convergence theorem, we can deduce the dominated convergence theorem. So then another important theorem in measure theory I'm going to tell you about is Fubini's theorem that was proved by Guido Fubini here. So this theorem now is about measurable function of two variables. So now you have the double integral of those functions, and again the point is to know whether the order of integration matters, and that's a problem about commutating the two integrals. So can we do this, yes or no? Fubini's theorem gives you sufficient condition under which you can indeed commute the two integrals, and so the order of integration does not matter. Now to conclude this video, I'm going to come back to all three theorems and give you two counterexamples. So first, that's going to be a counterexample to the monotone convergence theorem and the dominated convergence. So we are going to see that there are examples of sequences of measurable functions such that the integral of the limit is not equal to the limit of the integral. That's of course if the assumptions of the theorem are not satisfied. And we can use this first counterexample to build a second counterexample of a function, measurable function of two variables, such that the two integrals do not commute. So that means that for this function, we will see that the order of integration matters. If you change the order of integration, you are going to change the value of your double integral. So to illustrate the limitation of the Riemann integral, I'm going to look at this very simple probability problem. So the question is, what is the probability that a number chosen uniformly at random in the unit interval, by unit interval I mean the interval 0, 1, is a rational number? That's a very simple question, and using the basic tools from undergrad level probability theory, you can see that the random variable that is uniformly distributed in this interval is a continuous random variable, so it's characterized by a density function. And the way you find the probability that this random variable is rational is just by looking at the integral on the set of rational number of the density function. Okay, so more precisely, I'm going to call x the uniform random variable in the interval 0, 1. This random variable has density function phi, given by this is the indicator function on the interval 0, 1. So indicator function on a set, that's the function that is equal to 1 on this set and 0 on the complement of this set. So this function is indeed equal to 1 in the interval 0, 1 and 0 outside this interval. So that's indeed the density function of the random variable x. And then the probability we are looking for is exactly, so the probability that x is in the set Q, that's the integral on the set Q of phi of x dx, okay? Which we can rewrite as the integral of the indicator function on the set Q intersection 0, 1 of x dx. The function indicator function on Q is called the Dirichlet function. So notice that this function is discontinuous everywhere. So there are no known antiderivative of this function. And so the way you would compute this integral is really to go back to the definition of Riemann integral. So what is the Riemann integral of a function in general? How do we define that? So I'm going to show you here. So we have a picture of like a function. I intentionally take a smooth function that is a nice Riemann integrable function to show you how to compute or how to define the Riemann integral. So if you have such a function, and let's assume that this is the interval 0, 1 here, then to define the Riemann integral, you are going to first take a subdivision of this interval 0, 1. Okay? You take a subdivision into subintervals, and you are going to take a point in each of those subintervals. Okay? Then after, you can define, so this thing here is called a tagged subdivision. Okay, you have a subdivision of interval, but with a point in each. That's called a tagged subdivision. So to each tagged subdivision, okay, given your function, you can define what we call the Riemann sum associated to this tagged subdivision. And the way you define this is just by looking at this point. You look at the value of the function at this point, and you just draw a line here. At exactly the height is exactly the value of the function at this point, and you do that for each subinterval, and you end up with basically a collection of rectangles that looks like that. Okay, so you just look at the value and you look at all those rectangles, and you see that the sum of the area of those rectangles is kind of some approximation of the area under the curve. Okay, under the graph of the function. So that's supposed to be some kind of approximation of the integral. So of course, here the approximation is probably not very good because the length of those subintervals is pretty big. But the idea is just to take a sequence of tagged subdivision in such a way that the length of all those intervals goes to 0. Okay? And then you can look at the corresponding sequence of Riemann sum along this tagged subdivision. Okay, and hopefully this converges to a limit. Okay, so we are going to say that this function is Riemann integrable if the limit of the Riemann sum along any possible sequence of subdivision converges to the same limit. Okay, you want to have the same limit each time as long as the length of those subintervals goes to 0. Okay, it's clear that for this function that should be the case. Okay, so if indeed the limit of the sequence of the Riemann sum converges to the same limit regardless of the choice of the sequence of tag subdivision, then we say that the function is Riemann integrable, and the common limit of all the sequences of Riemann sum is going to be, by definition, the integral of the function, the integral in the Riemann sense. Okay? So now that we have redefined the Riemann integral, okay? How do we define the Riemann integral of a function? Now we can try to look at the integral of this weird function here. So I cannot draw that, of course, okay, because you have infinitely many like rational number and irrational number in the interval 0, 1, but you can kind of visualize that in your mind. Let's assume that now this very smooth function is replaced by this kind of very irregular function here. So, and let's take again a subdivision, a tag subdivision of the interval 0, 1. Okay, so no matter how you are going to choose your subdivision, here you have intervals, and all those intervals are going to contain infinitely many rational numbers and infinitely many irrational numbers. So, regardless of the choice of your subdivision, you can always choose all those points in those intervals to be all rational, in which case your corresponding Riemann sum is going to be equal to 1. At the opposite, you can also choose all these points to be irrational, in which case the corresponding Riemann sum is going to be equal to 0. So that means that no matter how you choose your sequence of subdivision, you can always choose those points here at the bottom in such a way that the sequence of Riemann sum is going to be equal to 0 all the time or equal to 1 all the time. So that means that the limit of the Riemann sum is going to depend on the limit of tag subdivision you are choosing, and so that means that by definition this function here, the Dirichlet function, is not Riemann integrable. Okay? And so because it's not Riemann integrable, the problem is not just that we don't know how to compute this integral. The theory just says that this integral does not exist. And so that means that this probability here does not exist. Okay? So conclusion, this probability, that is a very natural probability, does not even exist. And it's due to the fact that this function, the Dirichlet function, is not Riemann integrable. So now let's look at the basic definitions in measure theory, starting from the concept of sigma algebra. So first you start with a set omega that can be anything, and then a sigma algebra is going to be a collection F of subsets of omega. So collection of subset of omega that satisfy three conditions. So the first one is that omega belongs to F. Here there is no mistake. Omega indeed belongs to F, is not a subset of F, because omega, even if omega is itself a set, F is at some higher level. Okay, that's a collection of subsets of omega. So you want first omega to be part of the collection F. You want that if A is in F, then A complement is in F. And the first condition is that if you take any sequence of sets in F, then the countable union of those sets is again in F. So I insist here on the fact that we need to look at countable union only. You cannot look at uncountable union. That doesn't work for uncountable union. So you can summarize basically the definition of the sigma algebra by saying that you need three conditions that says that basically one, the full set is in F, two, F is stable by complement, and three, F is stable by countable union. Alright, so then next you can see that you can add more conditions that basically follow from that. For instance, if you combine 1 and 2, you see that omega is indeed in F, and so omega complement should be in F, which tells you that the empty set is also in F. Okay, so that's another condition you can add. Then you can also use the Morgan's law and see that the countable intersection is basically the complement of the union of the complement, okay? And so if you apply 2 and 3, you apply 2 and then 3 and then 2 again, then you get that countable intersections are also in F. Okay, countable intersection of elements in F is again in F. So you can say that the empty set is in F and F is also stable by countable intersection. In general, what you can prove is that if you take any countable collection of elements in F, then any operation, like basic operation on those sets, as long as the collection is countable, so by basic operation, I mean if you take any kind of union, intersection, symmetric difference, and so on, then the result is again to be in F. So that's stable by all those operations as long as the number of sets you are dealing with is countable. All right, so next, it's just a definition. Once you have a sigma algebra on a set omega, then the pair omega with its sigma algebra is called a measurable space, okay? And the elements of F are called measurable sets. That's because it turns out that with this definition, after we can define the notion of measure, and we can measure the sets that are in F, that are in a sigma algebra. Okay, so next definition, sigma algebra generated by a collection. So now let's assume that you start with an object that is similar to F here, that I'm going to call H. So H is again a collection of subsets of omega. But assume that this collection does not satisfy those three axioms. Then you can define something that I'm going to call sigma of H, that's the sigma algebra generated by H. That's basically the smallest sigma algebra that contains H. Okay? So often in practice, sigma algebras are defined like that. You just look at a very particular subcollection of subsets of omega, and you define a new sigma algebra. You define a sigma algebra as the sigma algebra generated by this collection of subsets. Okay, so you can easily prove that this sigma algebra indeed exists. The way you prove that is not very difficult. It's just by saying that sigma of H is basically defined as the intersection of all the sigma algebras that contain H. Okay? It turns out that if you look at an intersection of sigma algebras, you again end up with a sigma algebra. So the set of all sigma algebras is stable by intersection. Okay? And the only potential problem would be if this intersection is empty. Okay? But it's clear that the collection of all the possible subsets of omega is clearly a sigma algebra, and obviously it contains H. Okay, so you can write sigma of H as a non-empty intersection of sigma algebras, all the ones that contain H. That's going to give you again a sigma algebra, and that's by definition the smallest sigma algebra that contains H, that we call the sigma algebra generated by H. Okay, so a very natural example of sigma algebra that we use a lot in practice is called the Borel sigma algebra. Okay, and so this Borel sigma algebra is basically the one on the real line, but you can define that in some more general topological spaces, but I'm just going to look at the real line for now. That's basically the sigma algebra generated by all the intervals. Okay, so in this case, your set omega is just the set of real numbers. You can look at all the intervals in R, so that's everything of the form AB, for like interval AB for L less than B, okay? And you can look at basically the sigma algebra generated by that. So that's basically all the set that can be written as countable union, countable intersection, complement, and so on of a countable collection of intervals. Okay, so if you remember the Dirichlet function before, that was the indicator function on the set Q. Okay, so that's going to be useful after when we want to eventually solve our original probability prime. to use the fact that the set Q is in fact a Borel set. And indeed, we can prove that. So the proof is not very difficult. It just, the problem is just to be able to write the set of rational numbers using only intervals and those two operations here. So you see that by 3, okay, a countable union, okay, is going to be a countable union is of Borel set is going to be again a Borel set, okay, and because Q is countable, okay, to prove that Q is indeed a Borel set, the only thing we need to prove is that each singleton is a Borel set, okay, but the fact that a singleton is a Borel set, it's an easy consequence of the fact that the Borel sigma algebra is generated by the interval. If you take any real number x, okay, you can write x as the complement of the union of the interval negative infinity x and x plus infinity, okay? And so eventually, using this step, I mean using 3 but for only 2 sets and then 2, you can prove that each singleton is in your Borel sigma algebra, but then looking at the countable union of this singleton, you get that Q is in the Borel sigma algebra. So here is the proof. So first you use 1 and 2 to argue that the singleton X that you can write indeed like this is a Borel set. So here, this is indeed an interval, this is indeed an interval, so that's of this form here. So those two sets are in the Borel sigma algebra. By 3, the union is again in the sigma algebra, and by 2, the complement of this whole thing is again in the Borel sigma algebra. But you see that this set is basically all R except X, and so the complement of that is the singleton X, okay? Then, to conclude, you just use the fact that Q is countable, okay? And because Q is countable, you can just write Q as the countable union of its elements, and by using 3, you get that indeed Q is in B. So Q is equal to the union for X in Q of the singleton X, okay? That's simple, okay? That's by definition of the set, of any set. And here we can indeed conclude that it's in B because Q is countable, so this union is indeed countable. Alright, so that's going to be useful after to look at the Lebesgue integral of the Dirichlet function. So, next definition, that's the definition of a measurable function. So, now we have here the notion of a measurable space. Now you can define a function from a very theoretical, typically that's a very general measurable space, omega f, with value, so it can be again with value in any possible measurable space, but typically in probability theory, we are going to assume that this measurable space here is just the set of real numbers with its Borel sigma algebra. So we said that a function x going from omega to r is a measurable function if the pre-image of any Borel set by the function x, okay, which is defined as a subset of omega, that's the set of little omega in capital omega, such that x of omega is in B. For short, we are going to use this notation also in the future. That's the set where x belongs to B, is in F. So you want that each time you have a set B, a Borel set B in this Borel sigma algebra, then the pre-image of this set by x should be in F, okay? That's the definition of a measurable function. If you know about topology, that's kind of the same definition as a continuous function from a topological space to a topological space. A continuous function in topology is defined as a function such that the pre-image of any open set here is going to be an open set here, okay? Here the definition is the same, except that instead of moving an open set to an open set, you move a measurable set to a measurable set. All right, so then next definition, now we can define the notion of measure, okay? So we have our measurable functions, and I want to say that the word measurable function means that you can measure those functions, and by measuring those functions, I mean that you can basically compute their integral, okay? You can kind of think of the integral of a function as a measure of a function. So, but first, to be able to do that, you need to define an object that we call a positive measure that is only going to measure the sets in F. Right, so a positive measure is going to be a function mu defined on a sigma algebra F and with value in 0 plus infinity. Okay, so the plus infinity here is included. Okay, there is no mistake here. Plus infinity is a possible value of the measure. So for instance, we'll see after that the Lebesgue measure is basically the object that measures the length of those intervals, and clearly the Lebesgue measure of R is infinite. Okay, so infinity must be in the range of the positive measure. Okay, it's possible. Okay, so a function mu is going to be a positive measure if you need only one axiom, if it is sigma additive. And so sigma additive means that if you take a countable, exactly like here, you take a countable collection of subsets of F, then you know by axiom 3 that the union of this set is in F, okay? So the union here is again in F, so indeed you can look at mu of this union, okay? Notice that this function mu is not defined on omega. You don't look at mu of an element on omega, you look at mu of a set, okay? Because you want to measure sets. So mu of the countable union is indeed well defined because by 3 the countable union is indeed in F, and you want the measure of this countable union to be equal to the sum of the measure of the sets. This is true only if those sets are mutually exclusive. So basically they do not overlap, okay? So you can basically think of a measure. A measure is more or less the same as looking at the number of elements in a set. That's just a much more general object, but the cardinal of a set would have the same properties. And so there are obvious properties that you expect from a measure if you have in mind that a measure measures the size of the sets. You want, for instance, the measure of the empty set to be equal to 0. You want the measure of two sets A and B that overlap to be the measure of A plus the measure of B minus the measure of the overlap. Things like that. Okay? But we don't need to define all those properties as axiom. It turns out that only sigma additivity is going to be enough to generate all those other properties that we want. So basically, a measure is just something such that if you have sets that do not overlap, then the measure of all of them together, the union, is just going to be the sum of the measure of each of them individually. Okay, which kind of makes sense. Okay, intuitively, that's the kind of thing we want. So, next, just another definition, a little bit like measurable space here. If you have a measurable space and you define a positive measure on this measurable space, then you can eventually have a triplet of omega f mu, and this is called a measure space. Okay? And then last important definition that we are going to use to extend eventually the Riemann integral, it's the notion of Lebesgue measure. So the Lebesgue measure is going to be the unique measure on the Borel sigma algebra, such that the Lebesgue measure, like the measure of an interval AB, is just the length of the interval AB. So that's just B minus A. Okay? On the Borel sigma algebra or any sigma algebras, you can define multiple. There are an infinite number of possible measures you can define, but the Lebesgue measure is, in some sense, the most natural one. That's the one that looks at the length of the intervals, okay? So, the fact that there is uniqueness of this measure here, I'm not going to prove that, but kind of the basic idea behind that is the fact that the Borel sigma algebra is generated by the interval, and so by just defining your measure on the interval, that's enough to have a unique extension to the whole Borel sigma algebra, okay? But of course, you need some coherent definition for the measure of each interval so that eventually you can end up with a measure. So existence is not obvious, but the uniqueness is due to the fact that the Borel sigma algebra is generated by the interval, and so defining your measure only on the interval is enough to fully define your measure on all the Borel sigma algebra. So now that we have all those basic definitions, we are going to combine so the notion of measurable function, okay, and positive measure. And now we can use the measure not to measure the sets, but to measure the function, okay? And so now we are going to define the notion of integral of a measurable function with respect to a positive measure. So I'm going to do that in 4 steps, going from the simplest possible measurable function to a more complicated one. So first, we are just going to look at the integral of an indicator function, okay? So I'm taking a set A that is measurable, so that's a set A that is in our sigma algebra F. Here at the bottom, you can think of the horizontal line here as omega, and here, this is just the set of real number, and so the indicator function on A is just the function that is equal to 1 on the set A and 0 outside, okay? I'm just taking, like, in this case, a basic interval, but A can be anything, like, can be any measurable set. So, what should be the integral of that? I mean, what is a very natural way to define that? Well, you just said that there is an object, like the positive measure, okay, called mu, on the set omega that allows you to measure the set A. And the measure of the set A is mu of A, okay? Now, if you have a function that looks like that, it's kind of natural to say that the measure of the function is going to be some kind of area of this rectangle, okay? And here, because the range of the function is R, then you can just look at the length here, which is 1. Now, the problem is that this set here can be very abstract, but we have a measure on that measures the set. And so you can just say that the area of this function, or the area under the curve, or the integral, is just going to be the measure of A times 1. And that's it, that's the most natural definition. And that's indeed the way you define the integral of an indicator function. So here, yeah, I forgot to mention, we are going to think of the integral as a measure of a function rather than the measure of a set. And in general, in all my slides here, I'm going to assume that in general x is a measurable function, so defined on a measure space, and the measure is mu. Okay, so step 1, if you look at an indicator function, we are going to look at, so this rate's integral of the function, indicator function on A d mu, that's just going to be mu of A. Okay, so next set of functions we are going to look at are functions of this type that we call simple function. And so by definition, a simple function is going to be a function with a finite range. So the function can only take a finite number of values. And so that means that such function can be written as linear combination of indicator function. So in this case, that's going to be just A1 times the indicator function on the set A1 plus little A2 times indicator function on the set A2 and so on. Okay? So in this case, a very natural definition again, because it makes sense to, when we define an integral, to have some linear operator. Very natural way to define the integral of such a function is to say that the integral of this function, which is the integral of a linear combination, is just going to be the linear combination of the integrals. But the linear combination of the integrals looks at a linear combination of integrals of this type. So you can use step 1 to deduce the value of that. Okay? And so in this case, step number 2, the integral of a simple function. Okay, so that's something with finite range that you can write as a finite sum of ai times indicator function on sets, measurable set capital ai, d mu, is going to be the linear combination of integrals. But using again this definition, that's just the linear combination of the measure of the ai. Okay, so that's again natural definition. The definition guarantee that the integral is indeed a linear operator. So there is only one potential problem in this definition. It's the fact that if you look at this function, there are in fact many ways to write this function as a linear combination of indicator function. What you could do, for instance, is look at a1 times times the indicator function on the set a1 union a2, in which case you get a block like that. But then you add a little block on top here, saying that this block is obtained by adding a2 minus a1 times the indicator function on the set a2. So what I mean basically is that even if the way I decompose the function here is probably the most natural one, there are many different ways to write this function, okay? And so that the definition is coherent, what you really need is the fact that regardless of the representation of your simple function, the integral is always going to be the same. And indeed it's true, I'm not going to prove that, but the definition is coherent because of this property. If you take two different decomposition, two different expressions of your function, but you assume that the two functions are equal. So basically you have a sum of ai, indicator function on ai, equals sum of bj, indicator function on bj. Then the integral of this function by definition is going to be this. By definition, the integral of this function is going to be of the same way, but with instead bj and again bj here. Well, you can prove that if those two expressions, okay, even if the expression look different, if the two functions are indeed equal, then their integral are going to be equal. So that's coherent, okay? The definition is coherent. If two functions are equal, even if they are not represented in the same way, then using this definition, you will end up with two integrals that are equal. That's obviously what we need. If two functions are equal, their integral should be equal. Okay? So everything is fine. Next step, let's look at the integral of positive measurable function. It's possible in this case that the integral is infinite, it doesn't matter, okay? But we look now at positive measurable function, so that would be a function of this type, okay? But we assume that it's always positive. So in this case, we are going to try to define the integral of this function using step 2, so using our definition of simple function. And the motivation is going to say basically, and you can kind of see it in the picture here, I have a simple function under my curve here, and it seems that this simple function is pretty close to my positive measurable function. So here we are going to being motivated by the fact that it seems that a positive measurable function can be written as a limit of a sequence of simple functions. We are going to say that the integral of the positive function is going to be the supremum of the integral of the simple function over all the possible functions that are dominated by our original function. So more precisely, step 3 that gives you the definition of the integral of a positive measurable function says that if x is a positive measurable function, then the integral of x d mu is going to be the supremum over all s in the set of simple measurable function that is between, like sandwiched between 0 and x of the integral of s d mu. Okay, so you look at all the possible integral of all the simple functions that are dominated by x, okay, and you look at the supremum of that. Okay, so this definition is motivated by the fact that indeed, each time you have a positive measurable function, there exists a sequence of simple measurable function that converges pointwise to your function x. And this sequence is defined by xn of omega equals this weird thing here. But this weird thing is illustrated here. What I'm doing here basically is that I'm taking the real line here and I'm looking at a subdivision of the real line with intervals of length 1/2 at the power n. So when n is large, my subdivision is thinner and thinner. So I'm looking at a subdivision here, and I'm drawing all those lines here, okay? And then I'm just building all those rectangles here, a little bit like in the Riemann sum, except that now those rectangles are horizontal instead of vertical, okay? And so it's clear from the picture how you get this function xn, okay? It's exactly this. You look at 1/2 at the power n times the integer part of 2 at the power n times the value of your function. And you are going to get exactly all those rectangles that touch the curve here. So, of course, the point is that if this function x at some point goes to infinity, if this function x is not bounded, then your function xn is not a simple function, okay? That's going to take infinitely many values. That's why, instead of just looking at the function I drew here, you are going to look at the minimum of this function and n. So that means you cut at n, and you make sure that this function xn eventually becomes a simple function with only a finite range. Okay? So this function is indeed a simple function. So the integral of this simple function is defined in step 2. And because this sequence is going to converge pointwise to x, that kind of motivates this definition, okay? I'm not trying to prove anything here, okay? These are just definitions, that's the way Lebesgue defined things, and I'm just trying to explain that all those definitions make sense, okay? They are very natural, okay? But of course you cannot prove a definition, okay? That's just a choice, that's a modeling choice, but this modeling choice makes sense. So, now, last step is to define the integral of a very general measurable function. The point is that it's not going to work all the time, so we need to restrict to a set that we are going to call integrable function. Okay? But it turns out that the set of integrable function, from the point of view of the abstract integral or the Lebesgue integral, is much bigger than the set of integrable function in the Riemann sense. So now looking at integrable function, I'm going to do the following. I'm just going to use again, as in step 2, the fact that we want the integral to be linear. So, and we know already from step 3, we already have a definition of the integral of a positive measurable function. So what we do simply is that if we have a very general measurable function that can be positive and negative, then we are just going to decompose the function as a positive measurable function and minus another positive measurable function. And the two functions we use are just the positive part and the negative part. Okay, so if you have a function x, the positive part is the function that is equal to x when x is positive and 0 when x is negative. The negative part is the function that is equal to x, equal to negative x, if x is negative, okay? But equal to 0 if x is positive. So that means that both the positive part and the negative part are both positive. You can also prove that taking the positive part or the negative part, we still end up with a measurable function, okay? So that means that you can just write x as its positive part minus its negative part, okay? And then just say that the integral of the difference between positive part and negative part should be equal to the difference of the integrals, okay? So eventually we write that integral of x d mu is the integral of its positive part minus the integral of its negative part. And notice that those two integrals are well defined because x plus and x minus are both positive measurable functions. And so those two integrals are defined from step 3. All right. So now there can only be one potential problem. It's the fact that if your function x, so it's, one potential problem is that your function x is such that the integral of the positive part is infinite, and the integral of the negative part is also infinite, okay? It's possible at this step that the integral of a positive measurable function is infinite, but infinity is like a number. You can just say the integral is infinite. Now the problem is that if indeed the integral of both parts here are both infinite, then you end up with something that is undetermined, okay? You end up with an integral which is equal to infinity minus infinity, and we don't want that. And so we can easily define the integral of a very general measurable function, assuming that the positive part or the negative part has a finite integral, but instead what we are going to do is add more restriction, and we are going to assume that both the positive part and the negative part have a finite integral. Okay? So if it's the case, that means that the integral of the sum is finite, but the sum of the positive part and the negative part is equal to the absolute value of x. Okay? And so eventually we are going to define the set of integrable function, okay, as the set of function x such that the integral of the absolute value of x d mu is finite. Okay? This quantity here, integral of absolute value of x d mu, is basically a norm that we call the L1 norm, okay? And it's related, I'm going to give you another definition, to a topological space here that we call the Lebesgue space, L1 omega f mu. That's the set of functions that are integrable. So that's the set of function x that are measurable such that the L1 norm, this norm here of x is finite, okay? And so if you look at all those functions, then integral of the positive part and integral of the negative part are both finite, and so that means that for those functions, the integral of x d mu is well defined, okay? So now we have a complete description of the abstract integral from indicator function to more complex integrable functions. And so now we can use the Lebesgue integral, which what I mean by Lebesgue integral is basically this integral, but when mu is equal to the Lebesgue measure, to compute the integral of the Dirichlet function and answer our original probability problem. So for that, so let's go back to this slide. Okay, you remember that we proved that this integral does not exist. But now it turns out that the integral we just defined, but with respect to the particular positive measure lambda, which is the Lebesgue measure, then this integral with respect to the Lebesgue measure is a natural extension of the Riemann integral. So by a natural extension, what I mean by that is the fact that all Riemann integrable functions are Lebesgue integrable, and the Lebesgue integral of those functions is also equal to the Riemann integral. Okay, so the two integrals are equal on the set of Riemann integrable functions, but the set of functions that are integrable in the Lebesgue sense is much bigger, okay, than the set of functions that are Riemann integrable. So a natural way now to solve this problem is basically to go back to this probability, try to now compute this integral, but using the Lebesgue measure instead of using the basic Riemann integral. All right, so let's try to do this. So how can we do this? So obviously, again, we are not going to solve the problem by looking at some simple antiderivative. We need to be a little bit tricky, and so the idea in the background will be to use the fact that the Lebesgue measure or any positive measure is sigma additive. Okay, so because it's sigma additive, we kind of want to write this set Q intersection 0, 1, okay, as basically a countable union, okay, and that's possible because Q is countable, okay, so Q is countable, so that means that you can write this set, which is again countable, as the limit of a sequence of measurable sets, AN, okay, AN is basically x1, x2 up to xn, and I choose those xi in such a way that xi is different from xj, okay, for I different from j, okay? We know that this is possible because the set Q is countable, okay? Because the set Q is countable, it can be written as a limit like that. All right, so now, next step, let's try to look at the probability of this, like the probability that x is in Q. So now I'm just rewriting this integral, but d lambda, to underline the fact that we are no longer using the Riemann integral, for which this integral does not exist, but we use the Lebesgue integral, okay? And now you see that what we have to integrate is just an indicator function, okay? And we know from what we saw before that Q is a Borel set, okay? And also, obviously, the interval 0, 1 is a Borel set, so the intersection of the two is a Borel set. So this indicator function is indeed measurable. It's indeed a measurable function, okay? And it's bounded and everything, so the integral of this function d lambda, according to what we saw before, is well defined. Now we go from an integral that does not exist to an integral that exists. The last step is to compute this integral. Okay, and so for that, I'm just going to use, you see that just an indicator function, so I can just use step 1 of the construction of the integral and say that the integral of this indicator function d lambda is just the Lebesgue measure of the set Q intersection 0, 1, and that's it, okay? So that's just this, okay? And now, how can we compute this? Well, that's where I'm going to use sigma additivity. We have this collection here, AN, and so clearly this Lebesgue measure here, this set that's just the Lebesgue measure of the infinite union of the AN, okay? So that's just the infinite union of the AN, but the xi here are chosen to be different, and so I can just write the union of the AN as the union of its singleton xi, okay? Notice that xi is different from xj for I different from j, so that means that those singletons here do not overlap. That's important, even if they overlap, then this is still equal to that. But I need no overlap here to be able to use sigma additivity, okay? So that's the last step of the calculation. Lambda of the union, because those values are different, and so that means that those singletons here are mutually exclusive. Lambda of the union is going to be the sum of the Lebesgue measure of those singletons, and that's it. So we get this, okay, by sigma additivity, that's equal to the infinite sum of the lambda xi. Now, what is the Lebesgue measure of a singleton? Well, a singleton is like a degenerate interval. It's like xi, comma xi, closed on both sides. the length of this interval is just xi minus xi, which is equal to 0. So eventually, we end up with this probability is equal to infinite sum of zeros. That's again 0, okay? And so now, we were able to compute this probability using the framework of measure theory. Eventually, this probability is well defined, and we can compute it, it's equal to 0. Okay, so now, to conclude, before we go to the next step, I want to insist on the fact that I want to make two observations. So the 0 kind of makes sense, okay? Even if we didn't know all this theory, the 0 kind of is intuitively makes sense, is something that we want. So why is that? It's because the original problem says that we take a number uniformly at random in the unit interval. What is the probability that it's rational? Well, we know that the set of rational number is countable. At the opposite, the set of irrational number, its complement, is uncountable. Which means basically that there are way more irrational number than rational number. So that kind of makes sense to expect that if you take a number at random in the interval 0, 1, this number is not going to be a rational number, okay? So the value we get fits with our intuition. So the last remark I want to make before moving to the Kolmogorov model and modern probability is the fact that going from here to here, what we solve is not that, I mean, we were still not able to compute this integral, okay? This integral did not exist in the 19th century. It still doesn't exist today, okay? So the Lebesgue integral or the abstract integral in general does not allow you to compute those integrals. This integral doesn't exist. Now what we've done is we've defined a new integral for which the set of integrable function is much bigger. Okay, and so now we can have a new definition such that the integral of such a function exists, but still the problem in the 19th century wasn't about computing this integral. We did not know how to compute this integral. The problem was deeper than that. It was really that this integral did not exist. So now let's look at Kolmogorov's idea and how we can redefine some of the concepts from measure theory, but in the context of probability. So here I'm going back to the slide I already showed you with the main definition, like the main basic definition in measure theory, and we are going to see how all those definitions translate, but in the context of probability theory. So the only difference is that we are going to now assume that this set omega is interpreted as the sample space of an experiment, okay? So, for instance, if you roll 2 dice, you have 36 possible outcomes, 1, 1, 1, 2, 1, 3, and so on up to a double 6, okay? And those 36 outcomes, all together, they are going to represent the set omega. So, of course, omega can be much bigger than that, but that's just to illustrate what I mean by sample space, okay? So that's the set of all the possible outcomes of some experiment. That's in this context that we do some probability theory, and having this in mind, then we can define the notion of event, random variable, probability or probability measure, probability space, and expected value. Okay, these are like basic concepts that you probably saw at the undergrad level, but now we can define them from like similar definition in measure theory. So first, what is an event? Well, an event is going to be the same as a measurable set, which means that from the point of view of probability theory, the set of events should satisfy the 3 axioms of a sigma algebra. So the set of events form altogether a sigma algebra. So this makes sense. The first condition here would tell you basically that the fact that something happens, like anything, should be an event. The second one here says that if something is an event, okay, then the fact that this thing does not happen should be also an event. That makes sense. And this third property tells you that if you take a bunch of events, the fact that at least one of those events happen, which is exactly the set union of Vn here, should again be an event. Okay, so the fact that events are stable by complement countable union, but also countable intersection, and the fact that they contain omega or the empty space, and so on, makes complete sense. Okay, so that was Kolmogorov's idea to do this. Then, second concept of random variable. In probability, what we call a random variable is exactly the same as a measurable function. Okay, except that now your set omega is again a sample space. So going back to the previous example where, let's say, omega is the sample space associated to the experiment rolling 2 dice, we saw that there are 36 possible outcomes, and an example of random variable can be, for instance, x equal to the sum of the 2 dice. Okay? If you know the outcome of the 2 dice, let's call it omega, then x of omega is going to be a number between 2 and 12 that gives you the sum. All right, so random variable means measurable function. And so that means that the fact that x is in a Borel B should be in the sigma algebra F, which means basically that the fact that your random variable belongs to a set B is an event. Again, that makes sense. Going back to our example, for instance, if omega is the sample space associated to the experiment rolling 2 dice and x is the sum of the 2 dice, then the fact that x equals 7, the sum is equal to 7, should of course be an event. Okay? Then next definition, what is a probability? And instead, many times I'm going to use instead the terminology probability measure. So a probability measure is, in fact, a particular case. Is going to be for us a particular case of positive measure. Except that we've decided, okay, that's kind of a model assumption that a probability should be a number between 0 and 1. Okay? And so instead of having a very general positive measure, what we are going to impose is that our measure mu, that I'm now calling P for probability, is going to be defined on the set of events. Okay, so you look at, instead of looking at a measure of a measurable set, you look at the probability of an event. That's now going to be a number between 0 and 1. Okay, but except for that, the definition is the same. We need, of course, also to impose that P of omega, like the full set, is equal to 1. So that means that the probability that something, anything happens should be equal to 1. Okay? So, again, have in mind, a probability is a particular case of positive measure. So, in particular, that's sigma additive. Then, once you get your sample space omega, set of event F, and your probability measure, and you combine all three, you obtain a space that we call a probability space instead of a measure space. And then finally, let's look at the concept of expected value. So we saw that a random variable is the same as a measurable function. Okay? A probability measure is a particular case of positive measure. So that means that we can define the integral of a random variable with respect to our probability measure. This object is well defined, okay? At least when the random variable is integrable for that measure. And then this integral is going to be just what we call the expected value. Okay? So from the point of view of modern probability theory, the expected value of a random variable is just defined as the integral of this random variable with respect to the probability measure. So now let's look at the particular case of symmetric probability spaces and how computing the probability of an event in this case relates to combinatorics, which is the branch of mathematics related to graph theory also that is about counting rules. All right, so what is a symmetric probability space? Well, that's going to be a probability space such that the sample space omega is finite, okay? And we are also going to assume that all the outcomes are equally likely. So that's a very natural assumption in many contexts. So examples where this happens is when you flip a fair coin. In this case, you have two outcomes, heads and tails. Both outcomes should have the same probability, 1/2. If you roll a fair die, then you have 6 possible outcomes. They all have the same probability, 1/6. If you play cards with a well-mixed deck of cards, you have 52 cards. If you take a card at random, it's natural to assume that the card you are going to take is, for instance, the ace of spades with probability 1/52. In this context, it turns out that the probability of an event is simply the number of elements in this event, number of outcomes in this event, divided by the number of outcomes in omega. Okay? And this is something we can easily prove using just one simple axiom of probability, of a probability, which is sigma additivity. So, to prove this, let's first call P the common probability of all the possible outcomes in our experiment. So notice that here I'm using P of the singleton omega because strictly speaking, what goes here in the probability should be a set, not an element. So I'm looking at the singleton omega, and the assumption that all the outcomes are equally likely tells us that those probabilities should all be equal to the same value P for all possible outcomes omega. Okay? Then we can compute P explicitly using the cardinal of omega, using sigma additivity. So for that, I'm just looking at P times the number of elements in omega. I'm using this notation to say cardinal of omega, which is the number of elements in omega. So P times the number of elements of omega can be written in that way. So why is that? Well, all those probabilities are all equal to P, okay? So this sum is just equal to P times the number of elements in the sum, but we sum over all the little omega in capital omega, okay? So we have a sum of cardinal of omega terms, all of which are equal to P. So this is indeed equal to that. Then, implicitly in this notation, we mean sum over all the different omegas in capital omega, so that means that here all those singletons are mutually exclusive, and because of that we can use sigma additivity and rewrite the sum of the probabilities as the probability of the union. But the union of all the singleton little omega in capital omega is nothing else than just the full set omega. And by the definition of a probability, the probability of omega is just equal to 1. So from this, we deduce that P should be equal to 1 divided by the cardinal of omega, which we have here. So that shows that indeed, the probability of an event is equal to the number of outcomes in this event divided by the total number of outcomes in the special case where our event has only one outcome. So now to extend this result to all events, you just use again sigma additivity by summing over all little omega in an event A instead of all omega in capital omega, and we get the result. So the proof is just like that. You take any event A in your sigma algebra, then A can be written as the union of its singleton, okay? So P of A is P of this union. Because those singletons are mutually exclusive, they do not overlap. The probability of the union is just the sum of the probabilities. That's the axiom of a positive measure. That's sigma additivity. And then you end up with a sum of terms that are all equal to the same P here. And the sum is of size cardinal of A. Okay, you have cardinal of A terms in this sum. So that's just equal to P, the common value of those probabilities, times A, but we just proved that P is equal to 1 over the cardinal of omega. So eventually we conclude that P of A is equal to the cardinal of omega the cardinal of A divided by the cardinal of omega. Right, so conclusion, to compute the probability of A in this very common setting in practice, what we need to do is to be able to count the number of outcomes in subsets of omega, or in events, okay? And so for that, we are going to, I'm going to review like the 6 most common rules of combinatorics, 6 most common counting rules that are basically arrangement, permutation, combination, with or without repetition. So, arrangement is about choosing a subset and ordering the elements of this subset. So you basically take elements and order them at the same time. Permutation is only about ordering all the elements of the set. So we don't extract a subset, only the order is important, okay? And combination is about choosing a subset of a given set, okay? So permutation is about only ordering. In combination, what's important is the subset you are going to choose, but the actual order in which you are going to choose the element does not matter. Arrangement combines both. Each of the 3 possible operations can happen with or without repetition, okay? So, you can visualize all these rules by using those little blocks here, okay? So, when we have no repetition at the top here, I'm going to use blocks with always different colors, okay? There is no repetition of the same color. While here at the bottom, there is repetition of the same color, okay? You have many red, many blue, many yellow. Here you have 2 yellows. Here, same as in the first case. And to underline the fact that the order matters, for arrangement and permutation, I'm going to visualize that by extracting basically a row of blocks in a specific order. But to visualize, to have a picture that illustrates combination, I'm just going to take blocks that I'm going to organize like that, not in a row, to show that in fact the order here is not important, okay? So it turns out that those rules appear a lot in practice when you want to count the number of possible outcomes in some events, especially arrangements with or without repetition are pretty common. Permutation without repetition is common too, and combination without repetition. That's the 4 rules that are not very difficult to prove. The last 2 that are less common are a little bit more tricky. Okay, so first, let's look at the simplest case. That's the case of arrangement with repetition. Okay, so in this case, the goal is to look at the number of possible ordering of K blocks, each of which can be of n different colors. Okay, in the picture, I have n equals 3. I'm using 3 colors. Okay, there are repetition of the blocks, and I want to create a row of length 4. So K equals 4, n equals 3. So in this case, what is the total possible number of rows I can create? Well, that's not very difficult. You can just say, for the first block, I have n possibilities, because I have n colors, okay? Then for the second block, because I can repeat and reuse the same color, I again have n possibilities, and so on. So eventually, the total number of possibilities here is n times n times n times n, k times. That's exactly n at the power k. Okay, so that's our first formula. That's the simplest one, n at the power k. Then, second case, that is not very difficult, that's the case of arrangement without repetition. So in this case, I start with some blocks. There is no repetition of the colors, and I want to extract a subset of size 4 and order those elements. So in this case, n equals 6. I have 6 blocks with 6 different colors, and k is equal to 4, and I'm looking at the number of ordering of k blocks in general chosen from a set of n distinct blocks. So reasoning exactly like before, sequentially, by saying I'm going to choose a first block and then a second one and then a third one and so on, because the order is important. In this case, we end up by seeing that for the first block, because we have n possible colors, we have n possibilities for the first block. Okay? Then for the second block, because we cannot reuse the first color or the first block, we only have n minus 1 possibilities. And then for the third one, we have n minus 2 possibilities, and so on. And because we have to choose k blocks total, we end up with number of possibilities here is going to be n times n minus 1 times n minus 2 up to n minus k plus 1. Okay? And this thing can be simplified and we obtain this formula. So n minus 1 up to n minus k plus 1. That's the same as n factorial divided by n minus k factorial. I remind you, if you don't know, if you don't remember, that n factorial is just the product, when 1 times 2 times 3 up to n. Okay, so permutation now without repetition here is just a particular case of this one. Okay, it's just a particular case of that where n and k are equal. Okay, so we can redo the proof and saying that here we have 4 blocks with 4 different colors. We just need to rank all of them, order all of them. So in this case, we have n possibilities for the first block, n minus 1 for the second one, and so on, but we have to go down to 1. So eventually we get n factorial. That's a particular case of the previous formula. Okay? If you take k equals n, you get n minus n factorial, that's 0 factorial by convention. 0 factorial is equal to 1. So we get this one as a particular case of this one. Now, let's look at one of the most common continuous rule in probability. That's the case of combination without repetition. So in this case, we have different blocks with different colors, and we just want to extract a subset. So in general, we look at the number of subsets of k blocks chosen from a set of n blocks with different colors. In this picture, k equals 4 and n equals 6. Okay, computing the number of subsets here is a little bit more tricky than those 3 ones, but can be deduced from the previous two rules. Okay? The idea for that is to count the number of arrangements without repetition, okay? But in 2 different ways. So the first way is going to be like here, by choosing the blocks sequentially. Another way to count the number of arrangements without repetition is to say that we are going to directly extract k blocks simultaneously and only after order them, okay? And so what we get is the following. The goal is to find the number of combinations without repetition. Okay? N and K are defined like before. I'm going to call this number C and K. I'm also going to call A and K the number of arrangements without repetition, where we have n different colors and we want to order K blocks. So according to our previous reasoning, we saw that this number A and K is just equal to n times n minus 1 and so on, and you get n factorial divided by n minus k factorial. This expression is obtained by choosing the block sequentially, one after the other. Another way to count the number of arrangements without repetition is to say that first we are going to choose k blocks with no order from the set of n blocks, okay? The number of ways I can do that is exactly C and K, that's our unknown, okay? And then, step number 2, we still need to order those blocks. But we end up with K blocks, and we just saw that the number of ways we can order those K blocks that are distinct is K factorial. So that means that this number should also be equal if you instead choose the block simultaneously and then order them after. this number should also be equal to C n k times k factorial. Okay? So eventually we end up with two numbers that must be equal, even if they look different, but we just count the number of possibilities using different techniques, like different strategies. First, we choose sequentially. After, we choose simultaneously, and then only after order. This tells us that this equals that, and so that means that C n k is just n factorial divided by n minus k factorial times k factorial. So that's exactly the number of possible subsets of size k of a set of size n. So we can complete our table here, and we get that number of subsets of size k. This number is also written like this with big parentheses. You write that n choose k. Okay, this number is called n choose k. That's exactly the number of subsets of size k of a set of size n. Now, let's look at something a little bit more difficult, but that we can deduce from the case of combination without repetition. That's the case of permutation with repetition. So, in this case, you have blocks, okay, with a possible repetition of the color. Here I'm taking two yellow and one red, one blue. And the goal is to look at the number of ways we can order them. So, in this particular case, we have, using those notation, n1 equals 1 for red, let's say n2 equals 2 for yellow, and 3 equals 1 for blue. In general, we want to look at the number of possible ordering of n blocks such that you have n1 blocks with color 1, n2 blocks with color 2, up to nk blocks with color k. Okay. So, it turns out we cannot easily count the number of possible ordering using the same technique as here, choosing the block sequentially. So why is that? Well, let's look at just this very particular example. What is the total number of possible colors for the first block? Like the number of possible choices for the first block. We have 3 colors, so there are 3 choices. Okay? I have 3 possibilities for the first block. Now the problem appears already in this example for the second block. If we choose blue like we did here, or red for the first position, then we have 2 possibilities left for the second position. Okay? We have 2 possible colors left. We chose blue first. This one can be yellow or red. However, if we first choose yellow, okay, the color that appears twice here, then for the second block, we are going to have 3 possibilities, not 2. So you see that depending on what you choose at step 1, that's going to change the number of possibilities at the next step. And that becomes a nightmare to count all the number of possibilities here. So instead, the way you compute the number of possible permutation with repetition is by kind of having in your mind a line of n possible spots or n possible positions for your blocks. And step 1, you are going to choose n1 position, and you are going to put the blocks with color 1 there. And then you are going to choose n2 position among the remaining position for blocks with color 2, and so on. And if you do this, the counting becomes much easier, and you can eventually get an expression that depends on those n choose k. So, more precisely, we have the following. So, to count the number of permutations with repetition, just visualize a line like this with n dots that are the potential position for your blocks. Then, step 1, you are going to choose n1 position for the blocks with color 1. The number of possibilities, according to the previous formula we proved, is exactly n choose n1. Then you need to choose after n2 positions for your blocks with color 2. And for that you have n2 choose n minus n1 possibilities, because there are n minus n1 spots left. okay, and so on. And then eventually, you do this, choose n1 position for color 1, then n2 for color 2, and then you end up with nk for color k, and then you end up with this formula. It's n choose n1 times n minus n1, number of position left, choose n2, okay? Then n minus n1 minus n2, that's the number of position left after you put two colors, choose n3, and so on, and you end up with that, okay? So, now what's interesting is that if you look at this formula, it looks that we end up with an expression that is not symmetric in n1, n2 up to nk. While it should be, okay? It should be because things are symmetric, okay? In like n1, n2 up to nk. It turns out that if you compute explicitly this expression using the formula we proved before, n choose k is equal to n factorial divided by k factorial n minus k factorial, and you apply that formula for everything here, you have a lot of simplification, and eventually you end up with that number. It's just n factorial, which is the same as n1 plus n2 up to nk factorial, divided by n1 factorial, n2 factorial up to nk factorial. So this term, you see, is completely symmetric in n1, n2, nk. That makes sense. The prime is indeed symmetric in those numbers. Okay? So that's exactly the number of permutation with repetition. And so now we can again complete our table. The number of ordering of n blocks decomposed like that is equal to that number that we just saw. Another notation for that number is n choose n1, n2 up to nk. This one is called a multinomial coefficient. Okay, this is a binomial coefficient that's a multinomial coefficient. All right, so now let's look at the very last case, combination with repetition. That's the most difficult one. So in this case, we have a lot of blocks with as many blocks as we want from each color, and we want to take a subset. The order does not matter, but a subset of some given size. So in general, the problem is to look at the number of subsets of k blocks, okay? Each of which can be of n different colors. In this picture, n equals 3. You have 3 different colors, okay? And the number of blocks you take is equal to 6. So in how many ways? We can take 6 blocks total, okay? And each of them can be of 3 different colors. And the order does not matter. So this one is a little bit more tricky, but again, you can get a formula that is going to be computed from those n choose k. So to solve this problem, the idea is the following. So we want to look now at the number of combinations with repetition. So what we are going to do is call xi the number of blocks with color I in our subset, okay? So because there are n possible colors, okay, xi is well defined for I equals 1 to n. So we have n unknown here, x1, x2 up to xn. We have those n numbers. Now, because we take a total of k blocks, we know that the number of blocks with color 1 plus the number of blocks with color 2 up to the number of blocks with color n should be equal to k, okay? Of course, we take an integer number, a whole number of blocks, so that means that all those xi are natural number, okay? Can be 0, 1, 2, 3, and so on, okay? So they are integer. So the total number of combination with repetition is going to be exactly the number of solution of this equation, x1 plus x2 up to xn equals k, such that xi is an integer. So this problem is still not very easy, but it turns out that you can easily visualize the number of solutions of this equation if all those numbers are strictly positive. Okay, you don't want to have a number equal to 0 to be able to visualize that. And so to fix this problem, I'm just going to define a new quantity that I'm going to call yi, that's xi plus 1, that's going to force all the variables here to be strictly larger than 0, okay? So all the xi's are non-negative integer, but the yi become strictly positive integer. And clearly the number of solutions of the first equation is exactly the same as the number of solutions of y1 plus y2 up to yn equals n plus k. But now we have the new condition that yi is an integer that is strictly positive. That's the notation I use here. The star means that I remove 0 from the set. So maybe before going to the next step, I should explain this n plus k here. Well, you just replace the yi by their definition, okay? And you obtain x1 plus 1 plus x2 plus 1 up to plus xn plus 1, okay? But the sum of the xi is equal to k, and then you added 1 plus 1 plus 1 plus 1 n times. That's where the n comes from. So eventually, the number of combinations with repetition is just equal to the number of solutions of the equation sum of the yi equals n plus k, where yi is a strictly positive integer. So now, you can visualize those solutions by drawing a line like that. So I'm going to draw a little bit like here, a line with n plus k dots, okay? And I'm going to think of y1 as the size of a block of dots here. And then y2 as the size of another block of dots and so on. Okay? But because those numbers add up to n plus k, which is exactly the total number of dots we have, eventually you can visualize each solution of this equation by a sequence of blocks here, where you have exactly n blocks, and the total length of all the blocks is equal to n plus k. So for instance, you get this. So let's assume that y1 equals 3, then I draw a bar here at the third position, then y2 equals 4, so I'm taking 4 more dots, and so on, and I keep doing that, okay? And then that tells me that I can visualize each solution of this equation by choosing exactly, so n blocks, so that means n minus 1 bars here, okay, from a set of exactly n plus k minus 1 gaps in between those dots, okay? I have n plus k dots, so that means n plus k minus 1 gaps in between, okay? And to create n blocks here, I need to get to place here exactly n minus 1 bars. So that's basically the number of solutions of this equation, which is also the number of combinations with repetition. That's going to be exactly the number of ways I can choose n minus 1 bars from a set of n plus k minus 1 gaps. And by the case of combination without repetition, we know that this number is just equal to n plus k minus 1, choose n minus 1. And you can write it like that. That's n plus k minus 1 factorial divided by k factorial times n minus 1 factorial. And then eventually we can finish our table, and here we have the last formula for the total number of combinations with repetition. Now, in case the basic combinatorics rule we just saw are not enough for you to compute the probability of an event, because this event is too complicated, you can always use a Venn diagram to rewrite this probability as a function of probabilities of simpler events, okay? That hopefully you can compute using basic combinatorics. So what I mean by Venn diagram are basically pictures like that. In those pictures, ignore for now the tally marks, I'm going to explain what it means after, but the square is supposed to represent your sample space, omega, and the three circles here are like 3 events, okay? And you typically use this kind of picture of diagram to visualize your events and whether they overlap or not, okay? So you want to draw a picture that respects the overlap among those events, okay? And using those pictures, you can typically rewrite again probability of a complicated event as a function of probabilities of simpler events, okay? And so typically what happens in practice is that what you believe is intuitively true, like based on a Venn diagram, is indeed true, okay? And that follows from the axiom of a probability. So I'm just going to give you a few examples and eventually I'm going to end up with a very important formula that we use in probability theory to illustrate the use of Venn diagram called the inclusion-exclusion identity. So first, let's look at the empty set. Let's look at the probability of the empty set. If you think of a probability as a measure, the measure of the empty set, because that's nothing, should be 0, okay? And indeed, the intuition is correct. You can prove that the probability of the empty set is 0. That's easy to prove. You just use sigma additivity. You just say that because empty set intersection the empty set is equal to the empty set, that means that those, like a big collection of empty sets, are basically mutually exclusive events. So the probability of the union is equal to the sum of the probabilities. But then that means that the probability of the union, which is the probability of the empty set, is just equal to the probability of the empty set plus the probability of the empty set plus the probability of the empty set, and so on, okay? So the only possible solutions are probability of the empty set equals 0 or probability of the empty set equals infinity. But because your probability is between 0 and 1, the only possibility is probability of the empty set equals 0, okay? So that's the first thing. Another thing that is intuitively clear is that the probability of the complement of an event, meaning the probability that something does not happen, should be equal to 1 minus the probability that it happens, okay? And that's again something that you can prove using the basic axiom of probabilities. And the proof is just like that relies again on sigma additivity. You just say that P of A plus P of A complement, because those two events are mutually exclusive, and because their union is equal to omega, the sum here by sigma additivity is just equal to the probability of omega. But by definition, the probability of omega is equal to 1. And so you end up with probability of the complement is indeed equal to 1 minus the probability of your event, okay? This looks simple, but it's extremely useful in practice. In practice, there are many events for which the probability looks very difficult to compute, but looking at the complement makes things much simpler and suddenly becomes obvious, like what is the number of outcomes in this complement, in this event, okay? So, continuing along those lines, for something more complicated than just empty set or complement, what you see often in practice is problems where you have to compute the probability that at least one of n events occurs, okay? So, at least one of them, or the union of them, is typically an event that is difficult to understand, because that can mean exactly one of the n events, or 2 of the n, or 3 of the n, and so on. And so, counting the number of outcomes in a union of events is typically difficult. At the opposite, because that involves an or, okay? We want this to happen, or this to happen, or this to happen. And it's typically difficult to understand. At the opposite, it's much easier to deal with an and, okay? The probability that this and this and this happens, it's much easier. So, what I'm saying basically is that the probability of a union is very natural to compute. I mean, it's a natural thing that you want to compute, but it's typically difficult to compute. At the opposite, the probability of the intersection is easier. So you want to be able to turn your probability of union into probabilities of intersection, okay? And the formula that does that in math, it's called the inclusion-exclusion identity, okay? And here, I have an illustration of the inclusion-exclusion identity using only 3 events. So we have 3 events here, A1, A2, A3, let's say, and a natural way to try to compute the probability of the union would be to add the 3 probabilities, P of A1 plus P of A2 plus P of A3. If you do this, and step by step you are going to put a tally mark in all the outcomes you are going to count in your sum, you are going to have a tally mark here and here and here and here. And then again, here and here and here and here, and same here. Eventually, when you add up those 3 probabilities, you realize that you overestimate your probability, the probability of the union, okay? Because you counted twice outcomes in the overlap of 2 events, and you counted 3 times outcomes in the overlap of 3 events, okay? And so the next natural step would be to get rid of those extra tally marks here by removing P of A1 intersection A2, P of A1 intersection A3, and P of A2 intersection A3. Okay? If you do this, you get rid of 1 tally mark here, 1 here, 1 here, 1 here, 1 here, 1 here. You end up with this picture where you have indeed 1 tally mark in the overlap of 2 events, but you have no tally mark in the middle. Okay? So it seems that at this level, you basically underestimate the probability of your union, and that's easy to fix. You just eventually add the probability of the intersection of the 3 events. You count exactly once all the outcomes here, and then you end up with a picture where indeed you have 1 tally mark in all the possible subsets that altogether constitute the union of all 3. Okay? So this is not a proof, that's just an intuition, but it turns out that you can use a Venn diagram to kind of get formulas like those ones, and typically that works. Okay? So now let's give a proof of this formula, not for 3 events, but in general for n events. Okay? So the inclusion-exclusion identity typically says, in general says the following: if you have n events, okay, A1, A2 up to AN in your sigma algebra F, then the probability of the union is equal to this horrible double sum where you have this -1 at the power k plus 1 here, and you sum from k equals 1 to n. And then you look at this other weird sum here of probabilities of intersection of k events. So the sum here over I1 less than I2 up to less than IK means that you look at the sum over all the possible choices of k events, and you look at the probability of the intersection of those k events. Okay? So notice that in formula, this term is going to switch from 1, when k equals 1, to -1, then +1, then -1, and so on. Okay, that's why we call this formula inclusion-exclusion. And that appears here also in this picture. We said if we add up the probabilities, we overestimate, so we need to remove something. That's your minus sign for k equals 2. You remove the probabilities of intersection of 2 events. But then after that, you underestimate your probability. So you need to add something, and you add the probability of intersection of 3 events. That's your +1 here for k equals 3, and so on. Okay? So what the formula says in general is that the probability of a union of n events is equal to the sum of the probabilities of all events, okay, minus the sum of the probabilities of all possible intersection of 2 events, plus the sum of the probabilities of intersection of 3 events, and so on. And you keep going like that. Okay, that's what the formula says. Now, you see that the left-hand side looks simpler than the right-hand side. But in practice, like I told you, this means that A1 or A2 or A3 up to or AN occurs. This is difficult to conceptualize, while those intersections are typically easy. Okay, so typically we use this formula when we want to compute the probability of a union, and we have absolutely no idea of like what is the number of outcomes there, but we very much understand the intersection and the probabilities of the intersections. So how do we prove this? A typical proof is by induction, okay, but it's a little bit messy, so I came up with another simpler proof. Simpler in the sense that it's not as messy, but it relies on a little bit more sophisticated properties, and in particular to prove the inclusion-exclusion identity here, I'm going to use the fact that the expected value of a random variable is linear. So why is that? Well, we just define the expected value of a random variable as the integral of this random variable dp, okay, with respect to the probability measure, but by construction, the integral with respect to any positive measure is linear, okay? So that means that the expected value is linear. So we can use this properly to prove the inclusion-exclusion identity. So the first step of the proof is going to be to define a random variable, that's a measurable function, x, defined on your sample space omega with value in R. The definition looks complicated, but it's not that complicated, that just mimics this expression in the right-hand side. Here you have probabilities. So the right-hand side here is a number between 0 and 1. I want to turn that into a function, a measurable function, and so what I just do is that I replace the probability of this event by the indicator function on this event. So the function that is equal to 1 if omega belongs to the intersection, or 0 if omega does not belong to this intersection. Okay, so why does it make sense to do this? It makes sense to do this because if you look at the expected value of x, because the expected value is a linear operator, you can say that the expected value of this double sum is just the double sum of the expected values, okay? But the expected value of an indicator function, remember, expected value is integral of the function dp. Integral of an indicator function is just the measure of your set, and so in this case, because the measure, the underlying measure is p, the expected value of that is just the probability of this event, which is here, okay? So just by definition of the expected value, the fact that the expected value is linear, and the fact that the integral of an indicator function is just the measure of the set, from those three properties, we can deduce that the expected value of x is just the right-hand side here. Okay? So, to prove the inclusion-exclusion identity, the last thing we need to do is just to prove that the expected value of x is also equal to this probability, okay? Which means that basically x is going to be equal to 1 if omega is in the union, but equal to 0 if omega is not in the union. Okay, so that's the next step. To do this, I'm going to use an extra function that I'm going to call m, defined on omega, and this m of omega is going to keep track of the number of events omega belongs to. Okay, so the way it's defined is just like that. I'm just going to call m of omega the cardinal of I from 1 to n, such that omega belongs to ai. So in this picture, for instance, those tally marks, they are just a visualization of m. Okay? If omega is there, omega belongs to none of those sets. So m of omega is equal to 0. If omega is there, then omega belongs to exactly a1, but not a2 or a3. So m of omega is equal to 1. If omega is here, then that means that omega belongs to A1 and A3 but not A2. The overlap is 2, so m of omega is equal to 2. So those tally marks, they basically represent this function m. So to go from this picture to basically this one and prove that x is indeed the indicator function on this union, what we need to prove is that if m of omega is equal to 0, then x of omega is 0. But if m of omega is strictly positive, meaning that you are somewhere in the union, then x of omega is equal to 1. Okay, so the case where m of omega is equal to 0 is easy. If m of omega equals to 0, that means that omega does not belong to any of those n events. Okay, and so that means that this condition here is always false. So all those indicator functions are 0, and so all that is 0. Okay, so that's easy. Now the case where m of omega is strictly positive is a little bit more tricky. So to do this, and we are going to use a tiny bit of combinatorics to do that. So let's assume now that m of omega is strictly positive. So I'm somewhere in the middle here. So in this case, you see that all those indicator functions are going to be again equal to 0 if I'm looking at more than m events, because omega only belongs to m of those events. Okay? So that means that I can stop the sum here. The first sum, I can stop it at m. Okay? That's the first step of the proof. Then, second step of the proof is to count, to compute this sum here. But that's not that difficult, because if you look carefully, that's exactly the sum over all the possible choices of k events, such that omega belongs to indeed those k events, okay, is in those k sets. So the question is in how many ways we can choose k events, okay, such that omega belongs to those k events, and the answer is clearly m choose k. Why? Because exactly m of those events contain omega. Okay, so clearly the number of ways I can choose k of those events that all k contain omega is exactly m choose k. In like how many ways I can choose k of those m events. Okay, and so eventually, using those, we end up with that. If m of omega is strictly positive, okay, then I can stop the sum at m. Okay, here it's implicitly some m of omega. I'm just writing m to simplify, but it's like an m of omega. And we just saw that, so I'm rewriting this term, but we just saw that this sum here is just equal to m choose k, and that's it. So now the last step is to compute this sum. Something not fun in this sum is that it starts with k equals 1. We like sums that start from 0 in math, but that's easy to fix that problem. And also the k plus 1 is annoying. We prefer a k. That's easy to change. I'm just going to replace that by 1 minus the sum for k equals 0 to m of m choose k, and that's it. Okay? So what we do here is if we start the sum at 0, you see that for k equals 0, I have a negative 1 times m choose 0, which is negative 1, and so I compensate by putting a 1, and then I extract a minus 1 here, and that gives me that. Okay? And then, what is this sum here? Well, this sum looks complicated, but it's not, in fact, because that's the sum for k equals 0 to m of m choose k times negative 1 at the power k. I can multiply here by 1 at the power m minus k, and I make it clear that in fact this sum is of the form sum for k equals 0 to m of m choose k times a at the power k times b at the power m minus k. This, by the binomial theorem, is just equal to a plus b at the power m. In this case, a is equal to negative 1 and b is equal to plus 1. So this sum is just 1 minus 1 at the power m, that's 0 at the power m, that's 0. And so eventually you end up with just 1, and we are done, okay? We are done because now what we have is that if omega belongs to none of those sets, then x is 0. But if omega belongs to at least one of those sets, meaning the union, then x here is equal to 1, okay? And then that means that x, like we said, is indeed the indicator function on this event, which is the union of the events, okay? And then we conclude, like we said, by using the fact that the expected value is linear, and so eventually we get that the expected value of x here, that just expected value of this integer function, that's the probability of the union, that's also equal by definition of x to this expected value here. But by linearity, we said that you can move the expected value inside, this becomes a probability, and then we end up with exactly the inclusion-exclusion identity. Okay, now let's go back to general measure theory and look at the monotone convergence theorem and the dominated convergence theorem. So like I told you at the beginning of this video, those two theorems are going to be important later when we deal with stochastic processes, and in particular very important to prove theorems about martingales and Markov chain. So in both theorems, you start with a sequence of measurable functions. So now you have a very general measure space, not just a probability space. Mu is a very general positive measure. So you have omega f mu. All the xn's are defined on the same measure space with value in the real line with the Borel-Sigma algebra. Both theorems, the monotone convergence theorem and the dominated convergence theorem, are about whether you can exchange limit and integral. So more precisely, because we have a sequence now of measurable function, if you assume that this sequence converges pointwise to a limit x, then a natural question is whether the integral of the limit is equal to the limit of the integral. Okay? And both theorems have this same conclusion under different assumptions. So in the monotone convergence theorem, we need to assume some kind of monotonicity of the sequence. And so here we are going to assume that the sequence xn is non-decreasing. Okay? So we cannot define notion of monotonicity of just a function on omega, because omega maybe does not have a total order, okay? It's a very general set. So I'm not saying here that the function xn is monotone. I'm saying that the sequence of function xn is monotone. So that means that for all omega, xn of omega is less or equal than xn plus 1 of omega. So because of this monotonicity, that means that for all omega, xn of omega has a limit, possibly infinity, but it doesn't matter, and we can call this limit x of omega. Okay? So in the monotone convergence theorem, we don't need to assume pointwise convergence of xn to a limit x. The pointwise convergence is automatically given by the fact that the sequence is monotone. Okay? So we have again a sequence of non-negative measurable function with that is monotone. Then in this case, the limit of the integral is equal to the integral of the limit. Okay? Just an illustration of that, for instance, maybe you have x1 here, x2, x3, the whole sequence keeps going up, then you have a limit here, x. What the theorem says is that if you look at the integral of this function and the integral of the next function and so on, you have a sequence of integrals, then the limit of this sequence is equal to the integral of x. Alright, so the monotone convergence theorem has a slightly stronger conclusion, but the assumptions are different. Now, we replace the condition of monotonicity by a condition of domination. So in this case, because Xn is no longer monotone, it's possible in the general case that Xn does not have a pointwise limit, so we need to add that as an assumption. So the dominated convergence theorem assumes that Xn has a pointwise limit x, and the most important assumption is this. We assume that for all n, the absolute value of Xn is less than some other measurable function that is not just measurable but in L1. So that means that this measurable function y is now integrable. Okay? So again, that means that the integral of absolute value of y d mu is going to be finite. Alright, so if we have this condition of domination, then we have the same conclusion. Limit of the integral is equal to the integral of the limit. But we have another conclusion that says that the limit of the L1 norm of xn minus x is equal to 0. We'll see in the proof that this is a little bit stronger than this conclusion. So if we have that, then we easily deduce the second statement here. Okay? And again, a visualization of that, for instance. So here I have a sequence that intentionally is not monotone. So you see the function here go up on this side, but they go down on this side. So you don't have monotonicity of this sequence, but still the sequence is chosen in such a way that there is a limit x in bold here. Okay? And the condition of domination appears here. If you look at the dashed line, this function y here is represented here with the dashed line here. Okay, so that's a positive function. Let's say, yeah, that must be positive here in view of the condition. So that's your positive function here, and here at the bottom I drew also minus y. Okay, and so the picture shows that all those curves here, they are sandwiched between y at the top and negative y at the bottom, which means exactly that the absolute value of those xn are all less than this function y. Okay, so now how do we prove monotone convergence and dominated convergence? The proof is in 4 steps to get everything. First, we are going to start with a weak version of monotone convergence. Okay, same conclusion, but for a specific type of function. Then, from this first result, we can deduce the monotone convergence theorem. Then, step 3 is to use the monotone convergence theorem to get another important result in measure theory, not as important as those two ones, but still, that's called the Fatou's lemma. Okay? And then from Fatou's lemma, we can deduce the dominated convergence theorem. Okay, so first, let's look at this first lemma that we need to prove the monotone convergence theorem. So the lemma says that if you take a sequence an of measurable sets, so they are all in the sigma algebra F, and you assume that this sequence is non-decreasing, so non-decreasing for sets means that an is a subset of an plus 1 for all n, then in this case, if I have any positive measure nu defined on omega f, then nu of the union of those an is equal to the limit of nu of an. So I mentioned before that it's a weak version of the monotone convergence theorem. So why is that? Well, because this sequence is non-decreasing, the limit of an exists, and by definition, the limit of a non-decreasing sequence of sets is the union. Okay? So here you can read that as nu of the limit is equal to the limit of nu. So that's basically the same as monotone convergence theorem, but instead of looking at an integral, you look at a measure of a set instead of looking at integral of a function. So that's basically a particular case of monotone convergence, but for indicator function. Okay, having in mind that nu of an can be viewed as the integral of the indicator function on the set an d mu. Okay? So, again, that's just a particular case of monotone convergence theorem for indicator function. So, how do we prove that? Well, remember from the previous thing we did that when we have to deal with the measure of a set, we like to have a disjoint union. Okay, we want those sets here, if possible, to be mutually exclusive. Here, obviously, it's not the case. Okay, n is a non-decreasing sequence, so all those sets they all overlap. But then we can easily rewrite the union as a union of non-overlapping sets, and doing so, we can use sigma additivity. Okay, that's the idea of the proof. So, more precisely, we are going to do the following. I'm going to call S0 equals the empty set. We assume here that the sequence starts from n equals 1. So I'm just introducing a new set S0 that is the empty set. That's just to define the next thing. And then I'm going to define B1 as A1. Set minus the empty set, so that's just A1. B2 is going to be all the elements in A2 but not A1 and so on. So in picture, you get something like this. Maybe that's your sequence AN, so this is A1 here, A2, A3 and so on. And then the Bn are just like those rings here, okay? So that would be B1, what's here, it's going to be B2 and then B3 and so on. So you see from the construction, from the definition of the sequence Bn, that one, the infinite union of the Bn, okay, the union of all those rings, is also equal to the infinite union of the An, okay? But now those Bn do not overlap, okay? Those Bn by construction do not overlap. So that means that nu of the union of the Bn is equal to the infinite sum of nu of Bn. And that's what's going to make the proof work. So eventually, we look at nu of the union, okay? So that's the same as looking at the Bn instead of An. Okay, that's what we just said. Now I'm using sigma additivity to write the measure of the union as the sum of the measures. But then you see that this infinite sum is, by definition, the limit of the sequence of partial sum. So that's the limit when n goes to infinity of the sum of the measure of bk, but for k equals 1 to n. And then you can again use additivity to see that those bk here, they are mutually exclusive again. And the union of those bk, but when you stop k at n, that's exactly an. Okay? So that's equal to the limit here, but of this sum, but this sum is exactly nu of an. So we get the lemma. Okay? So that's step one. Now using this, we can deduce the monotone convergence theorem. So I just remind you the statement here. So to prove that the limit of the integral is equal to the integral of the limit, we are going to prove two inequalities. So the first one, the easy one, that the fact that the limit of the integral is less than the integral of the limit. So why is it true? Because of the monotonicity here. Xn is going to be less than x, okay? So that means xn is less than the limit of the xn. But the integral is a monotone operator, okay? So because xn is less than x, the integral of xn is less than the integral of x. And then you can take the limit on both sides. So that tells you that the limit of the integral, okay, is less than the limit of the integral of x, but this part does not depend on n, okay? So the limit doesn't matter, and so that tells you that the limit of the integral is equal to the integral of the limit. That's step one. So the details are here. By monotonicity, because you have xn less than x, integral of xn is less than the integral of x. You take the limit on both sides, but here the limit of that is just that itself, that doesn't depend on n, and so we have one inequality. The other inequality is a little bit more tricky to prove. So for that, we are going to fix some epsilon small, okay, and fix a simple function, sandwich between 0 and x, okay? And we are going to consider the sequence of sets an defined as, so these are subsets of omega, that's the set of omega such that xn of omega is larger or equal than 1 minus epsilon times s of omega, okay? I'm just using a short to say the set of omega such that we have this. So, now, we can compare this function xn with this new function here. The spirit of the proof is going to be after to say that, well, we can take the limit when epsilon goes to 0. And we can take the supremum over all the simple function s that are dominated by x. And by definition, this supremum is going to be, the supremum of the integral is going to be the integral of x. That's kind of the spirit of the proof, okay? So, step 1, we just write that integral of xn d mu is going to be larger than the integral of xn indicator function on an d mu. This inequality is obvious. I'm just injecting a function here in the integral that is equal to 0 or 1. So in particular, that's less or equal to 1. And so we have this inequality clearly. And then after, I'm going to use the fact that I'm going to look at the definition of an. And you see that by definition, on the set an, xn, this function here, is larger than 1 minus epsilon times s. So I can replace xn by 1 minus epsilon times s, but then of course I have an inequality. Of course I could not replace xn by this quantity here. I need for that to make sure that my omegas, they are all in an, so that this condition is satisfied. Okay? So we have this integral here, and then clearly this one, by linearity, okay, this last step is very easy, is just equal to 1 minus epsilon times the integral of s indicator function of an d mu. Alright, so then the next step is to look at the behavior of this sequence an and try to basically use this lemma. So let's look at the an. Let's assume that omega is in an. Then that means that xn of omega is larger than 1 minus epsilon s of omega. But because xn plus 1 of omega is larger than xn of omega, that's the condition of monotonicity here, that means that if this is true, then this is again true for xn plus 1, okay? And then that means that our omega eventually is in an plus 1. So what we just proved is if you take omega in an, then omega is also in an plus 1 by the monotonicity of this function. And so that means that an is a non-decreasing sequence, okay? So we are in the assumption of this lemma here. Then we still need here to understand like the infinite union of those an. So what is the limit of those an? So clearly if you take any omega in capital omega, you know that xn of omega for n very large is going to be close to x of omega, okay? But x of omega is larger than s of omega, okay? And so if you multiply this 1 minus epsilon, of course, your xn of omega is going to be larger than that eventually, okay? Again, you can say that if you take any omega in capital omega, for n large enough, xn of omega is going to be larger by definition of the limit x. Xn of omega is going to be larger than 1 minus epsilon times x of omega, but this quantity itself is larger than 1 minus epsilon times s of omega. So that means that for all omega in capital omega, omega belongs to an for n large enough. which means exactly that this sequence an is going to converge, is going to increase to a limit which is union of the an equals omega. Okay? So now the last thing to use this lemma is that we need to find a measure somewhere, and basically now I'm going to use the fact that nu of an defined as integral of s indicator function on an d mu is a measure. This thing is a positive measure. So I'm going to display all that. We just proved that because xn converges to x and increasing, an is going to increase to omega. And I'm using also the fact that if for all a in f, I define nu of a to be the integral of this simple function s, integral of a d mu, then I define a new positive measure. So how do we prove that this is a positive measure? Well, clearly it's obvious when s is equal to 1. Okay, let's assume, for instance, that s is just the function equal to 1 everywhere. Then that means that the integral of the indicator function on a d mu is just mu of a. So that means that nu is equal to mu. Okay? So now, how do you prove also that this is so yeah, if nu is equal to mu, of course nu is a measure, because nu is a measure. And now, how do you prove also that this is a measure for a more general simple function s? Well, by using the same thing I just said, but using also the fact that s is a linear combination of indicator function, and because the integral is linear, is a linear operator, the integral of the linear combination is the linear combination of the integrals, okay? And then from that you can again deduce that everything works fine, nu is indeed sigma additive, so that's a positive measure. Alright, so how can we use this now? What I'm going to do now is look at this quantity, and by using this measure, nu here, you see that this quantity here, this integral is just nu of an, okay? It's nu of an. I'm taking also the limit when n goes to infinity, like here, and so I have that the limit of the integral is going to be larger than 1 minus epsilon times the limit of nu of an, okay? But nu of an converges, like according to this formula, it's going to converge to nu of omega, okay? And that's how we are going to conclude. So first, we take the limit on this side. That's going to be larger than the limit when n goes to infinity of that, but that thing is just 1 minus epsilon times nu of an, okay, of the set an, so we get that. And because the sequence an is monotone and has limit omega, this part here is going to converge to nu of omega by the lemma. Here I'm using the lemma here, okay? But then nu of omega, if you go back to this function, that just converge to integral of s indicator function on omega, but this indicator function on omega, that's just the function equal to 1 everywhere, okay? So eventually we get that the limit of the integrals is larger or equal than 1 minus epsilon times the integral of the simple function s d mu. Alright, so now to conclude, notice that epsilon is a positive number but arbitrary number, so I can take the limit when epsilon goes to 0 on both sides. If I take the limit when epsilon goes to 0 here, I get rid of the 1 minus epsilon. And here, I do nothing, because that doesn't depend on epsilon. Okay? And then I can also take the supremum over all simple function s. And what I'm going to end up with here is exactly the definition of the integral of x d mu. Okay? And here, that doesn't depend on any simple function. Taking the supremum is not going to change this value. Okay? So, yeah, the way you conclude is take the limit when epsilon goes to 0 and the supremum over all simple function, and you end up with limit of the integral is equal to, or is larger or equal to the supremum of the integral of s d mu, and the supremum is over all the simple function s that are sandwiched between 0 and x. And if you remember the definition of the integral of a positive measurable function like x is defined as the supremum of the integral of all the simple function sandwiched between 0 and x. So that means that after taking the supremum, this quantity here, this integral here, just becomes integral of x d mu, which is here. Okay, so we are done. We are done eventually. We have that. We have here that the limit of the integral is less than the integral of the limit. But here we have that the limit of the integral is more than the integral of the limit. So that means that the limit of the integral is equal to the integral of the limit. Alright, so now, next step, let's prove Fatou's lemma. So Fatou's lemma is about sequences of positive measurable function. We don't have any assumption here on the monotonicity of the sequence. So that means that the sequence xn does not have to converge pointwise to a limit x. Okay? But the theorem does not study the limit of xn, it looks at the lim inf of xn. And the lim inf or the lim sup are always defined. And so the theorem says, the lemma says that the integral of the lim inf is less than the lim inf of the integral. So to prove that, that's a direct, so this follows from a direct application of the monotone convergence theorem, just having in mind the definition of the lim inf. So the lim inf of the sequence xn is defined, so for some specific omega, let's say, is defined as the limit when n goes to infinity of the infimum for all I larger than n of xi of omega. So that's basically the limit of the infimum on the tail of the sequence. So let's assume for now that we only look at the infimum here, not the lim inf, but just the infimum of the tail. Infimum for I larger than n of xi. When you increase n, you are going to look at some infimum over a smaller and smaller set, which means that the sequence of the infimum of xi for I larger than n is going to be non-decreasing. Okay? So that means that this function here, or I should say the infimum on the tail, is going to be a sequence that is monotone and non-decreasing. And so applying monotone convergence theorem to that, then we get exactly our result. Okay? So the proof is like that. So first, I'm going to call Zn this infimum on the tail of the sequence. So that's going to be the infimum for I larger than n of xi. You see that, again, when n increases, we look at some infimum on a smaller set of function, and so that means that this infimum is going to increase. Okay, when n increases, the infimum here increases too. Okay, so that means that, and you can also prove, I skip all the details here, but you can also prove that this infimum, the proof is not very difficult, this infimum of measurable function is again measurable. Okay, so that tells you that the sequence xn is a sequence of positive measurable function, and this sequence also is monotone, increasing. So you can apply the monotone convergence theorem to the sequence Zn. And now what you have to have in mind is that by definition the lim inf of the xn is exactly the limit of the sequence Zn. And then we are more or less done, okay? So then after, you can say that Zn has a limit. This limit is by definition the lim inf of the xn, and by using the monotone convergence theorem, eventually you get that the integral of the lim inf of the xn, okay, is equal to, by definition here, the integral of the limit of the Zn. Now I'm using the monotone convergence theorem to say that this integral is just equal to the limit of the integral of Zn, d mu, okay? Then when the limit exists, the limit is equal to the lim inf, which is also equal to the lim sup, so I can replace the limit here by the lim inf, and that's still the same. And then for the last step, I'm just using the fact that Zn, clearly by definition, that's the infimum over a bunch of functions including xn. So Zn is less than xn. Because Zn is less than xn, we have that integral of Zn is less than integral of xn. It's still true if you take the limit, okay? So we get indeed that integral of the lim inf is less than the lim inf of the integral. So that's Fatou's lemma, and now we can use this lemma to prove the dominated convergence theorem. So I keep the lemma here so that you see what we are going to use, and I remind you here the statement of the dominated convergence theorem. So, like I told you, this conclusion here is slightly weaker than this one. It's easy to deduce this from that, so the goal is to focus on that. So, in this case, what we are going to do, it's not completely obvious intuitively, like why we do that, but the trick to prove the dominated convergence theorem is to apply Fatou's lemma to the new function 2y minus absolute value of xn minus x. So, again, you can easily prove that because y, xn, x are measurable, this is again measurable. What's important is to check that indeed this function is positive, so that we can use Fatou's lemma. So, in this case, because of the condition of domination, that's still true in the limit. So not only absolute value of xn is less than y, but also the absolute value of x is less than y. But clearly this function is less than 2y minus absolute value of xn minus absolute value of x, but they are both, the two absolute values are less than y, so clearly this function is positive. Okay, so because it's positive, we can use Fatou's lemma, okay, which gives us the following. We have integral of 2y d mu. We start with this term. I'm putting the term in blue intentionally to compare with other quantities after. By definition, that's going to be integral of the lim inf of this function here. Okay, that looks a little bit artificial, but what I'm just saying here is that xn converges pointwise to x. That's the assumption of the dominated convergence theorem. So that means that this absolute value here goes to 0 when n goes to infinity. And so, because the limit of that is 0, in particular the limit exists, so you can look at the lim inf, and the lim inf of that is again 0. Okay? So, I'm just replacing 2y by something that looks much more complicated, basically removing a quantity that in the limit goes to 0. Alright, now, the reason why I'm doing that is to be in the situation where I can apply Fatou's lemma. Remember that this is a sequence of random variables. This is a sequence of measurable functions, sorry. I mean, it's still true for random variable, but we are looking at general measure theory now. So that's a sequence of measurable function that is larger or equal to 0. So by Fatou's lemma, the integral of the limit, the lim inf, is less than the lim inf of the integral. Alright, so then next step, I want to break this integral into two pieces. So I again get integral of 2y d mu, okay? This part does not depend on n. And now, just a little trick, I'm looking eventually at the lim inf of the integral of minus this part. You have to have in mind that the lim inf of minus something, that's the same as minus the lim sup, okay? Where the lim sup is defined like the lim inf, except that you look at the supremum instead of the infimum, okay? So that's easy to see. It's just like, for instance, the minimum of two numbers is the same as minus the maximum of minus those numbers. Okay, that's this kind of trick that we are using here. And so eventually you get that. That's equal to the integral of 2y d nu minus the lim sup of this integral here. But clearly, the function inside here is positive, so the integral is positive. Okay, so this whole part here is positive, and so eventually we get a quantity so basically this minus that is going to be less than just this quantity. So that's less than integral of 2y d mu. Okay, so it seems that here we turn into circle, but in fact we are almost done with the proof, because if you look carefully, the blue term, integral of 2y d mu appears here, but also appears at the end here. And so what this means is that this inequality here and this inequality there must be equations, in fact. Okay? So what we proved using this reasoning is that this is equal to that, because this is equal to that, everything in between is an equation. And so that means in particular that this term here is in fact not strictly positive. That's equal to 0. Okay? This term must be equal to 0. But this quantity here is exactly the L1 norm of xn minus x. Okay? So that says that the lim sup of the L1 norm is equal to 0. Obviously, that also means that the limit of the L1 norm is equal to 0, because the norm cannot be negative. Okay? So from that, we deduce that the lim sup of the L1 norm here is equal to 0, which proves the first part here. And to deduce the second part, that's not very difficult. You just look at the absolute value of this minus that. You want to prove that the absolute value of the difference goes to 0. So you look at the lim sup of the absolute value of the difference between those two integrals. And this, in fact, that's less than the lim sup of the L1 norm. So why is that? Well, that's because clearly absolute value of xn minus x is positive. It's a positive function because you take an absolute value. And so the integral of the absolute value is going to be more than the integral of the difference without the absolute value. And so you can put absolute value outside and that still works. Okay, just think about it. That's very easy, in fact. And so, in fact, we get that this absolute value here is going to be less than the L1 norm, which by definition is equal to that, but the L1 norm goes to 0 because we just proved that this term goes to 0. Okay, so that concludes the proof of the dominated convergent theorem. So now let's look at Fubini's theorem. So Fubini's theorem is no longer about sequences of measurable function, but about only one measurable function. But this function is now a function of two variables. Okay? And the main question is whether, looking at the double integral of this function, we can exchange the two integrals, of course without changing the value of the integral. So the question is, does the order of integration matter or not? Okay? So to define the framework of the theorem, and again, I'm not going to prove the theorem, the proof is too long, but at least I'm going to state carefully the theorem. To begin with, we need to have two measure spaces, omega 1 f1 mu1 and omega 2 f2 mu2. We know how to define a function on the Cartesian product omega 1 cross omega 2, okay, with value in R. The problem is that to be able to define measurability of this function, we need to also have a sigma algebra on the Cartesian product. And we don't have that yet, okay? Also, to be able to integrate this function, we need to integrate with respect to a measure, but we don't have any measure on some sigma algebra on the Cartesian product. So the first step is to define all that carefully, okay? So first, of course, we are going to look at a function defined on the Cartesian product that I'm going to call omega. Omega is omega 1 cross omega 2. That's just the set of all the little omega 1, comma, little omega 2. Okay? With omega 1 and omega 2 in capital omega 1, capital omega 2. We know how to do that. Now, the problem is that we do not have any sigma algebra on this set. And so the natural way to define a sigma algebra on this set using F1 and F2 is to look again at the Cartesian product of any measurable set in F1 and any measurable set in F2. The problem is that this collection of sets is not a sigma algebra. Sets that can be written as A1 cross A2, where A1 is in F1 and A2 is in F2, is called a rectangle, and the set of rectangle is not a sigma algebra, because clearly, if you look at the union of two disjoint rectangles, for instance, it's not a rectangle. It cannot be written as the Cartesian product of two measurable sets. So what we do instead is, it's simple, we just look at instead the sigma algebra generated by the rectangle. So, and we are going to call that the product sigma algebra. Okay, that's going to be a new sigma algebra F, now on the Cartesian product omega, okay, defined as F1 cross F2, and by definition, this is the sigma algebra generated by all the set of the form A1 cross A2, where A1 is in F1 and A2 is in F2. And this one is called the sigma algebra generated by the rectangles. So this set, for instance, here is a rectangle. So of course, if those two sets are not intervals, it doesn't look like a rectangle, like visually, but we still call that a rectangle. And again, this collection here is not a sigma algebra, but we can look instead at the sigma algebra generated by those rectangles. Okay, so that's the sigma algebra we are going to use. Now, how can we define now a measure mu on this product of two sigma algebras? Well, we use kind of the same trick. A natural way to define the measure of this rectangle, okay? Because we have an object here, mu1, that measures the size of A1, and another measure, mu2, that measures the size of A2. A natural way to define the measure of a rectangle A1 cross A2 is just to say that it's going to be mu1 A1 times mu2 A2. Okay? So a measure that satisfies that is called a product measure. Again, the problem is that we only have a definition on the rectangles, but because this sigma algebra is the sigma algebra generated by the rectangles, it turns out that there is only one measure called the product measure defined on this product here, such that the measure of a rectangle is just equal to the measure for mu1 of A1 times the measure for mu2 of A2. Okay, so that's the context of Fubini's theorem. We look at Cartesian product of sigma algebras like that, generated by the rectangles, and then this measure mu that is the product measure. Okay, so now with all that, if we take a measurable function, okay, on the new measure space omega f mu, then we implicitly define a measurable function, okay? So a measurable function of two variables, let's say little omega 1 in capital omega 1 and little omega 2 in capital omega 2. And of course, we can also define the integral, like the single integral of x of omega d mu, okay? Now the question is that implicitly, any little omega in capital omega is in fact a pair of two omegas in those two sets. So you can also view the function x as a function of two variables, and the question is whether integrating this function with respect to mu1 and then with respect to mu2 is the same as integrating with respect to mu2 and then integrating with respect to mu1. The answer is yes, but under some assumptions. So the first assumption is an assumption on the measure space omega f mu that is called sigma finite. So the first assumption of the theorem is that the measure space omega f nu must be sigma finite. So sigma finite just means that the set omega can be written as a countable union of measurable sets with finite measure for the measure mu. Okay, so an example of measure space in which the set omega has infinite measure, but still the measure space is sigma finite, is just the set R with the Borel sigma algebra and the Lebesgue measure. In this case, it's clear that R can be written as a union, a countable union of intervals with length 1. So that means with Lebesgue measure 1. So the Lebesgue measure of those sets is indeed finite, and R, the whole set, can be written as a countable union of those sets with finite Lebesgue measure. So again, R with the Borel sigma algebra and the Lebesgue measure is an example of sigma finite measure space. Then, if we impose this condition on this set and some condition on the function x, not defined yet, but that's going to be a function x defined on the Cartesian product here, again with the product sigma algebra, and we use the product measure. Under some condition on this function, then we can indeed exchange the two integrals. So more precisely, we have the following theorem called Fubini's theorem. We take a function, a measurable function from omega f mu to R with the Borel sigma algebra. Again, that means that the pre-image of any Borel set here by the function x is going to be in this sigma algebra. Okay? And then we are going to assume that first, this set omega f nu is sigma finite. Okay, we have the definition here, and we are also going to assume that the function x is either positive, measurable, or integrable. Okay, so if the function is positive, everything is fine. It's possible that the double integral is equal to infinity, but again, that doesn't matter. Okay, we would just get infinity equals infinity. Or another case is when the function is integrable, so that means again that the integral of the absolute value of x d mu is finite. So in those two cases, the two integrals commute. So that means that the double integral of x, d mu1, d mu2, so you can look at the integral with respect to mu1 first, and then the integral with respect to mu2, so that's basically first coordinate, second coordinate, is equal to the same double integral, but where you now integrate with respect to mu2 first and then mu1 after. Okay? So those two integrals are equal. That's what we want to use most of the time in practice, and it turns out that those two integrals are both equal. Another way to express that, they are both equal to the single integral, but this time on omega, which is the Cartesian product of x d mu, where mu is your product measure. Now, to conclude this video, I'm going to come back to monotone convergence theorem, dominated convergence, and Fubini's theorem, and the goal is to find counterexamples to those theorems. So, the goal is to find first a sequence of measurable functions such that the integral of the limit is not equal to the limit of the integral. The point of finding a counterexample like that is to show that the assumptions of the theorems are important. If they are not satisfied, it's possible that you cannot exchange limit and integral. Second, we are going to use the first example to build a second counterexample, but this time a counterexample to Fubini's theorem, and find a function that basically, a function of two variables, such that the double integral of the function changes if you change the order of integration. So that means that the order of integration matters. Again, the goal is to show that the assumptions of Fubini's theorem are important. It's possible that the conclusion is not true if the assumptions are not satisfied. Okay? And so here are the two examples. On the left, you have an example of a sequence of measurable functions. I'm going to explain that shortly. And here you have basically some kind of representation of a function of two variables. In both cases, our set omega, or in this case omega 1 and omega 2, is just R, okay? So we are just going to take something simple. We don't need to be sophisticated in the choice of the measure space. It's just the real line with the Borel sigma algebra and the Lebesgue measure, okay? So in this case, the Lebesgue integral is just going to be the same as the Riemann integral. Those functions are Riemann integrable, there is no problem, okay? Same story here, except that now we are, in the case of two dimensions, we have two variables, and so now omega is going to be R squared, okay? Again, the sigma algebra is going to be the sigma algebra generated by the actual rectangle in R2, and our measure is just, again, the Lebesgue measure, but cross itself in two dimensions, okay? So, things are easy to compute. You don't have to do complicated integral. It's just looking at areas in this case and volume in this case. You have to think of that as a three-dimensional picture. So, first, let's look at this sequence of measurable functions. So, how is it defined? I'm just going to call x0 the function that is equal to 2 between 1/2 and 1. So that's like 2 times an indicator function between 1/2 and 1, okay? Then x1 is equal to 4, but between 1/4 and 1/2. x2 is equal to 8, between 1/8 and 1/4, and so on. Okay, so you understand how this is constructed. So basically, to go from one function to the next one, you are going to divide the length here by 2, but you are going to increase the value of this function on its support by 2. So you are going to multiply by 2 the value of this function. All right. So before we prove that in this case the integral of the limit is different from the limit of the integral, let's check first that this sequence indeed does not satisfy the assumption of the monotone convergence theorem or the dominated convergence theorem. So why is it true? Well, clearly the sequence is not monotone, okay? You see that the function x1 is larger than x0 on this set, but x0 is larger than x1 on this set, okay? So you cannot compare the function, none of them is larger or smaller than the others, okay? So the assumption of monotonicity is not satisfied. Now, second question is, can we find a measurable function that dominates all of them? Well, because they are disjoint supports, the smallest possible function that dominates all of them, that's the sum of all of them, okay? So that's the function equal to 2 on this interval, but then that jumps at 4 on this interval and 8 here and so on. And so, what is the integral of this function? Well, you just compute the area under the curve. Here, the length here is 1/2, but the height here is 2. So that means that the integral of x0, okay, the Lebesgue integral of x0 is just equal to 2 times 1/2, that's 1. Then here, it's the same story. The area here of this rectangle is the same as this one. You divide the base by 2, but you multiply the height by 2. So eventually, you get that the integral here is again 1, and 1, and 1, and 1, and so on. Okay? So that means that the integral of the sum, okay, of all of them, the sum of all of them would be the smallest function that dominates all of them, is just going to be equal to, so the integral of that is just going to be equal to 1 plus 1 plus 1 plus 1 plus 1 plus 1, and so on. Okay? So the smallest function that dominates them have integral equal to infinity, which means that this function is not integrable. So that means also that this sequence does not satisfy the assumption of the dominated convergence theorem. Okay? So now, how can we compute the limit of the integral? Well, implicitly, we already did that. I told you that the integral of x0 is just the area here, which is 1. integral of x1 is again 1, x2 it's again 1, and so on. So they all have integral equal to 1, okay? So that means that the limit of the integral is equal to the limit of just 1, so the limit is 1, okay? That's the first thing we can say, okay? So limit of the integral with respect to the Lebesgue measure is equal to 1. So now, to compute the integral of the limit, what we need to do first is to understand the limit of xn. What is the pointwise limit of xn? Then, if I take any omega negative, clearly xn of omega is equal to 0 for all n. Okay? So that means that xn of omega in this case is just constant equal to 0, it goes to 0. Same if omega is larger than 1. Now, if I take any omega positive, okay, even small, I can find n large enough such that, you know, the sequence 1, 1/2, 1/4, and so on, that's the sequence 1/2 at the power n. So I can find an n large enough such that 1/2 at the power n is going to be smaller than this little omega. And so that means that for all n larger than this n such that 1/2 at the power n is less than omega, we are going to have xn of omega equals 0. Okay? So eventually we end up with, if you take any omega outside the interval 0, 1, then xn of omega is always equal to 0. But if you take any omega in this interval, eventually, so this strictly positive omega is going to be larger than a 1/2 at the power n, and after that n, xn of omega is again equal to 0. Which means that for all omega on the real line, xn of omega converges to 0. Okay? So that means that xn has a pointwise limit equal to 0, but of course, the integral of 0 is equal to 0. And so we end up with integral of the limit is equal to 0, which is different from 1, which is the limit of the integral. Okay? So that gives you a counterexample where if the sequence is not monotone, and if the sequence is not dominated by an integrable function, then it's possible, you see, that the limit of the sequence of integrals is not equal to the integral of the limit of the sequence. Alright, so now, let's look at this example now. What this picture means is that we now have a function that I'm going to call x. It's a function of, let's say, omega 1 here, omega 2, okay? Omega 1 and omega 2 are just real numbers. And we assume that if omega 1 is between 1/2 and 1, and omega 2 is between 1/2 and 1, then your function x of omega 1, omega 2 is equal to 4, okay? Then if you look at the function on this rectangle, when omega 1 is there and omega 2 is there, then the function is equal to -8, and so on, okay? So, notice that this example is built from this one. You can see that here, the 1/2, 1, 1/2, 1 is the same as the support of x0. And the 4 is the same as 2 times 2, okay? And so, you can view the value of your function on this square as x0 of omega 1 times x0 of omega 2, okay? Then, same story on this rectangle. On this rectangle, you have here on the interval 1/4, 1/2, you have that corresponds to the support of this function x1, and again the 1/2, 1 is the support of the function x0. And also, if you look at the values of x0, x1, where they are positive, that's 2 and 4. But 2 times 4 is 8 here. So, this function x on this rectangle is defined as the product x1 of omega 1, no, I should say minus x1 omega 1 times x0 omega 2. Okay, and then you keep going like that. Okay, so that's basically x0, x0 minus x1, x0, x1, x1 minus x2, x1, and so on. That's how we build this counterexample. So again, like before, let's check quickly that this function x does not satisfy the assumption of Fubini's theorem. Remember that for Fubini's theorem, we need the function to be either positive or integrable. So clearly here, the function is not positive. Okay, it's positive here on this diagonal of square, it's positive, but on the rectangle just above, that's negative. Okay, so that does not satisfy this assumption. What about integrability? If we look at, again, the product measure obtained by taking two Lebesgue measures, well, the integral of the function on this square, you have to kind of visualize that looking at a three-dimensional picture where you have the square here, but then the function has value 4, and then it has value 8 here, and then 16, and so on. So the value of the integral on this square is exactly the volume of some kind of cube or whatever. So the value is 4, but the size of the square is 1/2, this length here, times 1/2, okay? So the area here is exactly 1/4, but the value of the function is 4. So that means that the integral of the function on this square only is 4. Then, to compute the integrals on the other square or rectangles, that's the same idea as here. To go from this square to this rectangle, you divide by 2 the area of the shape. You divide by 2, you divide by 2, you divide by 2, and so on. But at the same time, you multiply the absolute value of the function by 2. So that means that the integral on this square is 1, but the integral on this rectangle is again 1. And the integral on this square is again 1, and so on. Okay, so that means that the double integral, okay, of, let's say, d omega 1, d omega 2, of your function x, or absolute value of x, is going to be equal to 1, plus 1, plus 1, plus 1, plus 1, and so on. And so eventually, the integral of the absolute value, so absolute value turns your negative 8 into an 8, and the negative 32 into a 32, and so on, is just going to be the sum 1 plus 1 plus 1 plus 1 plus 1 infinitely many times. That's equal to infinity. So that means that this function x is not integrable either. Okay, so the assumption of Fubini's theorem are not satisfied, so it's possible that the two integrals do not commute. So now let's look at the double integral of this function. So how do we do this? Well, first I'm going to fix some omega 2 here. Omega 2 is there. I'm going to fix an omega 2 and look at the integral of x omega 1 omega 2 d lambda omega 1. Okay? So I'm looking at basically a section like that, and I want to compute the integral of this function of two variables, but only in this direction, in the direction of omega 1. So how can we do this? Well, that's not very difficult. You can just look at the length. I mean, the shape of the function is not very complicated, so you can just see that the integral is going to be the length here, which is 1/4, times negative 8, plus the length here, 1/2, times 4. Of course, 1/2 times 4 plus minus 1/4 times 8 is 0. Okay? So, same if you look at a line here or a line here, it doesn't matter where you choose omega 2, the integral of x omega 1 omega 2 d omega 1 is always going to be 0. Okay? Again, that's because to go from this square, any square, to the rectangle on the left, you divide the area by 2, but you multiply the value of the function by 2 with a minus sign. So that compensates, And so that means that the integral is equal to 0. So the double integral of x is going to be 0 if you integrate first with respect to omega 1. Okay? So we get this eventually. I forgot to show that, but if you have a line here that add up to 0, that was to explain that 1/4 times -8 plus 1/2 times 4 is 0. And so eventually we obtain that the double integral, d omega 1, d omega 2, you integrate with respect to omega 1 first, is equal to 0. Now, what about the double integral of x, but if we integrate first with respect to omega 2? So in this case, at the opposite, I'm going to fix omega 1 and look at the value of the integral of x of omega, but only d omega 2, and see what's going on. So if you do this, following the same reasoning as here, for any omega 1 between 0 and 1/2, you are again going to cross a square and then a rectangle. The rectangle is twice the size of the square, but the value on the rectangle is half of the value on the square. So again, you obtain 0. Okay? So double integral of integral of x of omega d omega 2 for any omega 1 between 0 and 1/2 is again going to be 0. But, and I can draw that here like this, okay? This line is going to cut, again, 1/4 times 16 minus 1/2 times 8, that's 0. Same everywhere here. Except that, look at what's happening here. The way this is built with square on the diagonal rectangles above, that means that each horizontal line here is going to cross a square and a rectangle, okay? Regardless of the value of omega 2. At the opposite, if you look at all the possible vertical lines here, they are going to also cross a square and a rectangle on the left of 1/2. But on the right of 1/2, you only cross this square, which means that now the integral of x of omega, but d omega 2, okay, for omega 1 in this region, so I'm looking again at integral of x of omega 1, omega 2, d omega 2, for any possible omega 1 in this interval, 1/2, 1, this integral is going to be equal to, when you look at the vertical line, and the way you compute the integral is just by multiplying this length by this value. This length is 1/2, this value is 4, 1/2 times 4 is 2. So, what we just proved here is that the integral of x of omega d omega 2 is the function equal to 0 on the left of 1/2 and 2 on the right of 1/2. That's exactly x0. Okay? x0 is exactly this function that is equal to 2 on the right of 1/2 and 0 on the left of 1/2. So the integral of x omega d omega 2 is equal to x0. And so this double integral, but d omega 2, d omega 1, is now going to be the integral of x0, and we saw before that it's equal to 1. And so eventually, this is x0 omega 1, and so eventually you conclude that the double integral, but this time d omega 2, d omega 1 is equal to 1, which is different from 0. So that gives you an example of function for which the order of integration matters. That's all for today. Thank you for watching. In the next video, I'm going to cover chapter 2 of my stochastic modeling book about conditional expectation and distribution of a random variable.